Welcome to the Late Lab. It's good to have you here tonight. Before anything else, where in the world are you watching from? Maybe you're tucked into bed with the lights turned low, half listening beneath a blanket. Maybe you're on a late journey somewhere, watching the dark slide past a window. Or maybe you're simply resting on the sofa, pretending that this is definitely not the fourth video you have watched instead of going to sleep. Wherever you are, hopefully the room is calm, the day is softening around the edges and your thoughts are beginning to slow. If you enjoy these quiet journeys through science, a like and subscribe would be deeply appreciated. It helps this little corner of the internet keep drifting along, one strange idea at a time. And to everyone already subscribed, thank you. Truly. Your support makes all of this possible, and it means more than can be neatly tucked into a single sentence. Now, tonight's subject is one of those ideas that sounds almost too strange to be real, which is always slightly inconvenient when trying to relax. Quantum field theory asks us to look beneath particles, beneath atoms, beneath the familiar solidity of tables, stars, hands, and cups of tea, and imagine reality as something made from fields that stretch everywhere. Quiet, invisible fields filling space, vibrating in precise ways, and giving rise to the particles that make up the world. So there is a small risk that this topic may keep the mind gently wandering for a while. But with any luck, it will do so in the best possible way, like watching moonlight ripple across dark water and realizing the surface is only part of the story. So let's begin, shall we? What is quantum field theory, and why does modern physics suggest that the universe may not be made from tiny things at all, but from fields beneath everything? At first glance, the world seems to be made of things. A stone is a thing, a leaf is a thing. A cup on a table looks like a small solid object resting on a larger solid object, both of them quietly agreeing to stay where they are. Even the air, though invisible, can be imagined as countless tiny molecules drifting, colliding, and spreading through a room. This is the familiar picture of reality. The universe appears to be filled with little pieces of matter moving through space. Sometimes they bump into one another, sometimes they stick together, sometimes they fly apart. It is a useful picture, and for everyday life it works beautifully. It helps explain falling apples, thrown balls, flowing water, boiling kettles, and the very important mystery of why walking into a closed door is not recommended. But at the deepest levels modern physics has tested, this picture is not quite the final one. Quantum field theory is the modern framework behind much of particle physics. It describes reality not mainly as tiny isolated objects moving through emptiness, but as fields spread throughout space. In this view, what are usually called particles are better understood as local excitations of those fields. An electron is not simply a tiny bead sitting somewhere in the universe. A photon is not merely a small pellet of light flying through darkness. A quark is not just a miniature speck hidden inside a proton. Each one is connected to an underlying field. There is an electron field. There is a photon field, more commonly understood as the quantum form of the electromagnetic field. There are quark fields. There are neutrino fields. These fields are not present only where a particle happens to be detected. They extend throughout space. An electron appears when the electron field is excited in a particular way. A photon appears when the electromagnetic field is excited in a particular way. The particle is what the field looks like when it produces a small countable event. That idea is strange, but it is not meant to make reality less real. A table remains real. A cup remains real. A toe remains regrettably real if the table leg finds it in the dark. Quantum field theory does not say the familiar world is fake. It says the familiar world is built from something deeper and less intuitive than ordinary objects. A field, in physics, is something that has a value at different places in space. A simple comparison is temperature in a room. Near a radiator, the air may be warmer. Near a window, it may be cooler. Temperature is not a little object hiding in one corner. It is a condition spread across the room. Wind across a landscape works in a similar way. It may be still in a valley, quick over a hill and swirling around a building. The wind has a pattern across space. Quantum fields are far more subtle than temperature or wind, but these comparisons help open the door. A field does not have to be a hard object. It can be a spread-out physical reality, able to change from place to place and influence what happens. In quantum field theory, the fields themselves are quantum. Their excitations come in discrete amounts, and those discrete excitations are what experiments often detect as particles. This shift from particles to fields did not arrive suddenly. For centuries, particle-like thinking made sense because matter looks particle-like. Isaac Newton described motion with extraordinary success. His mechanics explained how objects move under forces, why planets orbit, and why falling bodies accelerate toward Earth. Newton also treated light partly as if it were made of tiny corpuscles, small particle-like units. The universe could be imagined as matter moving through space according to clear mathematical laws. Yet even Newton's picture contained a quiet puzzle. Gravity seemed to act across empty space. Earth pulled on the moon. The sun pulled on Earth. The equations worked with magnificent precision, but the deeper mechanism was not obvious. How could one object reach across nothing and influence another? Newton himself was careful about this question. The mathematics described what gravity did, but the physical picture still had shadows around the edges. The field idea became much stronger in the 19th century through Michael Faraday. Faraday pictured electric and magnetic effects using lines of force. Around a magnet, iron filings arrange themselves into graceful curves, revealing a hidden pattern in the surrounding space. Faraday treated those patterns as more than a drawing trick. He saw them as evidence that space around magnets and electric charges had physical structure. James Clerk Maxwell then gave Faraday's vision mathematical form. Maxwell showed that electricity and magnetism were joined parts of a single electromagnetic field. His theory revealed that changing electric and magnetic fields could travel as waves. Light itself was understood as an electromagnetic wave moving through space at a definite speed. This was a major turning point. Empty space was no longer just a blank stage where objects performed. It could carry fields. It could carry waves. It had properties that mattered. The background of reality was beginning to look active. Then Albert Einstein changed the picture again. In 1905, special relativity showed that the speed of light in a vacuum is not just the speed of light itself. It is a fundamental speed limit built into nature. No usable signal can travel faster. Space and time are not fixed in the old familiar way, but depend on motion, while the speed of light remains the same for all observers. Any deep theory of matter and light had to respect that limit. It could not allow causes to leap instantly across the universe. It had to combine quantum behavior with relativity. Ordinary quantum mechanics was astonishingly successful for atoms, spectra, and many microscopic systems, but it was not enough when particles moved near light speed, or when energy could turn into new particles. Quantum field theory grew from this need. It brings together quantum mechanics, special relativity, and fields. It allows particles to be created and destroyed while preserving the deep conservation laws of physics. It explains why particle-like events appear in detectors while still treating fields as the underlying reality. So the reason fields come before particles in modern physics is not that particles are useless. Particles remain essential in experiments. A detector records a click. A photon is absorbed. An electron is measured. A track appears after a collision. These are real events. but the deeper description is field-based. The particle is the local expression. The field is the wider thing being expressed. This changes the meaning of solidity. A table feels firm because atoms resist being pushed into one another through electromagnetic interactions, because electrons follow quantum rules, and because fields settle into stable patterns. The table is not solid because it is made from tiny hard grains touching in a simple mechanical way. It is solid because quantum fields and their interactions create stable matter at human scales. That is the calm strangeness at the heart of quantum field theory. The world does not become less real when examined closely. It becomes more layered. The empty spaces between things are not merely blank. The particles inside things are not quite little pebbles. The forces between things are not invisible strings tugging through nothing. Instead, reality appears as a vast arrangement of fields, spread everywhere, usually quiet, sometimes excited, and capable of producing everything that looks particle-like, solid, bright, or tangible. The old picture of objects moving through emptiness was a necessary step. But beneath that picture, modern physics finds something deeper. The cup still rests on the table still holds it up, the room still feels ordinary. Yet underneath the ordinary scene, quantum field theory suggests that the universe is speaking in fields. A field begins as a simple idea, though physics has a habit of taking simple ideas and quietly making them enormous. In ordinary language, a field might mean a stretch of grass, perhaps with sheep in it, standing around as if they are waiting for a committee meeting to begin. But in physics, a field means something more abstract and much more powerful. A field is a quantity or condition that exists across space, with a value at each place. It is not just one object sitting somewhere. It is a spread-out pattern. Temperature in a room is a gentle example. One corner may be warmer because sunlight is resting on the floor. Another corner may be cooler because it sits near a window. The temperature is not a tiny bead travelling through the room. It is a value that can be different from place to place. If someone could map it carefully, the room would have a temperature field, a quiet, invisible landscape of warmth and coolness. Wind gives another useful picture. Across a hillside, the air may move slowly near the ground, faster over open grass, and differently again around a wall or a tree. At every point, the wind has a direction and a speed. That pattern across space is a field. It is invisible until something reveals it, like leaves twisting, dust drifting, or a hat deciding it has had enough of its owner. Gravity can be described in field language too. Around Earth, there is a gravitational field. At each point around the planet, an object would feel a pull toward Earth's centre. Near the surface, that pull is strong enough to keep feet on the ground, oceans wrapped around the globe, and dropped biscuits on a tragic downward journey. Farther away, the field weakens, though it never simply switches off like a lamp. The moon feels Earth's gravity, and Earth feels the moon's gravity. The field gives physicists a way to describe influence across space without imagining a physical string between objects. This was one of the great changes in scientific thought. Instead of asking only what objects were doing, physicists began asking what space around those objects was like. That may sound subtle, but it changed the shape of physics. Space was no longer merely an empty container. It could have conditions in it. It could hold patterns. It could carry influence. Michael Faraday was one of the people who made this new way of thinking feel physically real. Faraday worked in the 19th century and had an extraordinary gift for imagining invisible processes. He studied electricity and magnetism not just as forces that jumped from one object to another, but as effects carried through the space around them. To help picture this, he used the idea of lines of force. A magnet makes this beautifully visible. Scatter iron filings around a bar magnet, and they arrange themselves into curved patterns. The filings trace in visible order. They reveal that the region around the magnet is not featureless. Something about that space guides the filings into shape. Faraday saw these lines not as imaginary decorations, but as clues to real physical structure. The magnetic field around the magnet could be treated as something meaningful in its own right. This was a profound shift away from simple action at a distance. In older pictures, one object might seem to pull or push another across empty space with no clear machinery in between. Faraday's field lines suggested that the in-between mattered. The space between objects was not passive. It could be filled with a field, and that field could explain how influence was transmitted. Faraday did not express all this through the most advanced mathematics of his time. His strength was physical intuition, experiment, and visualization. But his ideas gave later physicists something precious to build upon. One of them was James Clerk Maxwell, who took Faraday's field picture and gave it a mathematical body. Maxwell's work on electricity and magnetism was one of the great unifications in the history of science. Before him, electricity, magnetism, and light could seem like related but separate phenomena. Electric charges attracted and repelled. Magnets had poles and field patterns. Light travelled as waves. Maxwell showed that these were deeply connected. Electricity and magnetism were different aspects of one electromagnetic field. In Maxwell's theory, a changing electric field can produce a magnetic field, and a changing magnetic field can produce an electric field. The two are woven together. They can sustain one another and travel outward as waves. When Maxwell calculated the speed of these waves, he found that it matched the known speed of light. This was not a small coincidence politely sitting in the corner. It was a revelation. Light itself appeared to be an electromagnetic wave. That means a beam of light is not merely something moving through space. It is a travelling disturbance of the electromagnetic field. When sunlight crosses the distance from the sun to Earth, it is not carried by tiny invisible wheels or some cosmic postal service. Though that would be charmingly inefficient. It is an electromagnetic wave moving through space at light speed, with electric and magnetic aspects oscillating together. Maxwell's equations became one of the most elegant achievements of classical physics. They showed that fields could do more than describe static pushes and pulls. Fields could ripple. They could carry energy. They could carry momentum. They could move through space as waves. The universe was already becoming stranger than a simple collection of objects. A classical field, then, is not quantum yet. It does not involve uncertainty in the deep quantum sense. It does not come in particle-like excitations in the way a quantum field does. But it prepares the mind for that later step. It shows that physics had already learned to take invisible spread-out realities seriously. Long before quantum field theory, the field had become a central character. The experimental confirmation came through Heinrich Hertz in the late 19th century. Hertz produced and detected electromagnetic waves in the laboratory, showing that Maxwell's mathematical prediction was not just beautiful theory. The waves were physically real. They could be generated, transmitted, and received. The same underlying principles would eventually lead to radio, television, radar, wireless communication, and the many invisible signals now passing through rooms so quietly that only the router seemed stressed about it. Hertz's work helped close the loop between mathematics and experiment. Faraday had imagined lines of force. Maxwell had built the theory of the electromagnetic field. Hertz showed that electromagnetic waves could actually be made and measured. The field was no longer just an elegant idea. It was a working part of physical reality. This classical field revolution reshaped what physicists meant by emptiness. A region of space might contain no obvious matter, no dust, no air, no visible object, and yet still contain fields. It might have an electric field, it might have a magnetic field, it might be crossed by electromagnetic waves. A field could store energy even where there was no solid object. It could carry effects from one place to another without anything like a thrown stone travelling between them. That is why field thinking was such an important bridge toward quantum field theory. It trained physics to accept that the deepest ingredients of reality may not always look like small objects. Sometimes the more fundamental thing is the pattern spread through space. The local object, the visible motion, or the detectable event may be only one expression of a wider field. Classical fields made nature less mechanical in the old simple sense, but more coherent in a deeper sense. They turned invisible influence into something with structure. They joined electricity, magnetism, and light. They showed that space could carry waves and energy. And they quietly prepared the way for an even stranger idea, that fields themselves might obey quantum rules. Light had already been given a beautiful classical explanation. Thanks to James Clerk Maxwell, it could be understood as a wave in the electromagnetic field, rippling through space with electric and magnetic parts woven together. It was elegant, powerful, and deeply satisfying. For a while it seemed as though light had finally been placed neatly in its proper drawer. Then nature quietly opened the drawer again and made a mess. The trouble began with heat. Every warm object gives off electromagnetic radiation. A piece of iron placed in a fire first glows dull red, then orange, then yellow-white as it becomes hotter. The same basic principle appears in stars, light bulbs, heated metal, and even the faint infrared glow coming from the human body. Anything with a temperature above absolute zero emits radiation, though not always in a form human eyes can see. Physicists wanted to understand this glow precisely. One important ideal case was called blackbody radiation. A blackbody is not necessarily a black object in the everyday sense, but an idealized object that absorbs all radiation falling on it and emits radiation according to its temperature. It is a beautifully simple concept, at least until the mathematics gets involved and begins rearranging the furniture. Classical physics could explain parts of the blackbody spectrum, but not the whole thing. It struggled especially at short wavelengths, where the old theory predicted that a hot object should emit an impossible amount of high-energy radiation. This failure became known later as the ultraviolet catastrophe, a wonderfully dramatic name for what was, in essence, a calculation going badly wrong. Classical physics seemed to imply that heated objects should pour out unlimited energy at ultraviolet wavelengths, which they plainly do not. Kitchen ovens are many things, but they are not tiny portals of infinite ultraviolet doom. The problem was not that the experiments were careless. Measurements of blackbody radiation were becoming increasingly precise. The problem was that the classical assumptions underneath the theory were not matching reality. Light, heat, and matter were refusing to behave as smoothly as expected. Max Planck found a way through the problem in 1900. Planck was not trying to overthrow physics for fun. He was trying to solve a very specific puzzle. To make the observed blackbody spectrum come out correctly, he proposed that energy was not exchanged in a perfectly continuous flow. Instead, it was exchanged in discrete packets. The amount of energy depended on the frequency of the radiation. Higher frequency radiation came in larger packets, while lower frequency radiation came in smaller packets. This was the quantum hypothesis. The word quantum simply means an amount, or a discrete portion. Planck's idea suggested that energy exchange had a kind of graininess to it. Not grainy like sand in a shoe, thankfully, but grainy in the deep mathematical sense that nature seemed to use fixed steps rather than an infinitely smooth ramp. At first, Planck treated this cautiously. It was a strange move, and it was not yet the full quantum revolution. But it worked. It matched the black body radiation curve. It solved the ultraviolet catastrophe by preventing energy from being distributed in the unlimited way classical physics had allowed. The door to quantum physics had opened, even if nobody yet knew how far it would lead. Then Albert Einstein pushed the idea further in 1905. He studied the photoelectric effect, a phenomenon in which light striking a metal surface can knock electrons out of that surface. Classical wave theory suggested that brighter light should gradually supply more energy to electrons, and that enough intensity should eventually free them. But the experiment showed something more particular. The colour or frequency of the light mattered crucially. Below a certain frequency, no electrons were ejected, no matter how intense the light was. Above that threshold, electrons could be released almost immediately. Einstein explained this by treating light as if it arrived in particle-like packets of energy. These packets were later called photons. In his explanation, each photon carried an amount of energy linked to its frequency. If the photon did not carry enough energy, it could not free an electron from the metal, even if many such photons arrived. If it did carry enough, it could transfer that energy in a single interaction. This was deeply unsettling, because Maxwell's theory had shown that light behaved as a wave in the electromagnetic field, and that was still true. Light diffracts, interferes, and travels like a wave. Yet the photoelectric effect showed that light also behaves as if it comes in individual packets. It was not simply one thing or the other. Light had become the first great bridge between classical fields and quantum particles. This did not mean Maxwell was wrong in any simple sense. Maxwell's electromagnetic theory remains one of the great achievements of physics. It describes countless behaviors of light and electromagnetism with remarkable success. But Einstein's work showed that a complete account of light also had to include quantum behavior. The electromagnetic field could not remain purely classical forever. Somehow, the field itself had to be connected to discrete quanta. The same kind of quantum thinking soon entered the atom. Niels Bohr proposed a model of the atom in 1913 that used quantum rules to explain why atoms emit and absorb very specific colours of light. In classical thinking, electrons orbiting an atomic nucleus should radiate energy continuously and spiral inward. Atoms should be unstable. But real atoms are stable, and when they interact with light, they produce distinct spectral lines. Bohr suggested that electrons could occupy only certain allowed energy levels. They did not radiate continuously while in these stable states. Instead, they emitted or absorbed light when moving between levels, with the light carrying the energy difference. This helped explain why hydrogen, for example, produces specific lines in its spectrum rather than a smooth rainbow of every possible colour. Bohr's model was not the final picture of the atom. Later quantum mechanics would replace its neat little orbits with a deeper description based on wave functions and probabilities. But Bohr's idea was another sign that nature was not behaving continuously at small scales. Atoms exchanged energy in definite steps. Light arrived in quanta. Matter and radiation seemed to be following rules that classical physics had not anticipated. This is still not full quantum field theory. The full theory would come later when physicists learned how to combine quantum mechanics, fields, and special relativity into one framework. But the seeds were already here. Blackbody radiation showed that energy exchange could not always be smooth. The photoelectric effect showed that light, the great wave of Maxwell's electromagnetic field, could behave like a stream of quanta. Atomic spectra showed that matter absorbed and emitted light in specific quantum jumps. Light had refused to stay in one category. It was a wave, clearly and experimentally. It was also quantum, clearly and experimentally. This did not make it confused. It meant the older categories were too small. That is why light sits so close to the beginning of the quantum story. It forced physics to accept that the electromagnetic field, once understood as a smooth classical wave, had a hidden quantum structure. A beam of light crossing a dark room can be described as a wave in a field. But when that light interacts with matter, it can arrive in indivisible packets, one photon at a time. The universe had not abandoned order. It had revealed a deeper kind of order, one that came in steps, probabilities, thresholds, and quanta. The classical field was still there, graceful and powerful. But beneath its smooth surface, something discrete was stirring. Light had already shown that the universe was not going to fit neatly into old categories. It behaved like a wave when it spread, interfered and diffracted. It behaved like a particle when it exchanged energy in individual photons. That alone was strange enough. But then physics discovered something even more unsettling. Matter did it too. The familiar world makes matter feel solid and definite. A pebble seems like a little object. A grain of dust seems like a smaller object. An electron, it was tempting to imagine, might simply be smaller still, a tiny bead orbiting inside an atom. Shrink the scale far enough, and perhaps reality would become a collection of minute pieces, all moving in precise paths like a very serious cosmic clockwork. Quantum mechanics did not allow that comforting picture to survive unchanged. One of the central ideas that emerged was wave-particle duality. This does not mean that an electron is sometimes a tiny ball and sometimes a water wave, changing costumes when nobody's looking. It means that the categories of wave and particle, taken from ordinary experience, are not deep enough. Matter and light show wave-like behavior in some experiments and particle-like behavior in others. They're not fully described by either familiar image alone. Louis de Broglie made one of the boldest steps in this direction. In the 1920s, he proposed that if light, long understood as a wave, could also behave like particles, then perhaps matter, long understood as particles, could also behave like waves. Electrons and other particles, he suggested, should have wavelengths associated with them. This was not a poetic metaphor. It was a physical claim with consequences. If matter had wave-like properties, then electrons should be able to produce interference patterns. Interference is one of the clearest signs of waves. When two water waves meet, they can reinforce one another or partly cancel out. Light does this too. In the right experiment, light passing through two narrow openings forms a pattern of bright and dark bands, places where waves strengthen or weaken each other. If electrons also formed interference patterns, then matter itself would be revealing wave-like behavior. That is exactly what experiments found. The double-slit experiment became one of the most famous demonstrations of quantum behavior. When particles such as electrons are sent toward two narrow slits, and a screen records where they land, each electron is detected as a small localized event. It appears in one place, like a particle. But when many electrons are sent through, even one at a time, the pattern that gradually builds up is an interference pattern. It resembles the result expected from waves passing through both slits and overlapping. This is where the ordinary imagination starts to fidget. Each electron is detected as a single event, yet the overall distribution behaves as though wave-like possibilities have interfered. The electron is not simply a tiny pellet choosing one path in the familiar way. Quantum mechanics describes it through a wave-like structure of possibilities, and only when a measurement is made does a definite outcome appear. Erwin Schrödinger gave quantum theory one of its most important mathematical tools, the wave function. The wave function is not a simple physical wave sloshing through ordinary space like a ripple across a pond. It is a mathematical description of a quantum system, encoding the probabilities of different possible measurement results. For an electron in an atom, the wave function helps describe where the electron may be found and what energy it may have. It does not describe a tiny planet orbiting a tiny sun in a neat little circle. This helped explain why atoms are stable and why they emit and absorb particular colours of light. Electrons in atoms are described by allowed quantum states rather than classical orbits. Their behaviour produces the spectral lines seen in glowing gases and starlight. Those lines are not decorative cosmic barcodes, though they do look suspiciously like the universe labelling its own ingredients. They are evidence of quantum structure inside matter. Werner Heisenberg added another essential piece with the uncertainty principle. It is often described as saying that measurement disturbs what is being measured, but that is only part of the story and can be misleading if taken too casually. The uncertainty principle is not mainly about clumsy instruments. It is a real feature of quantum systems. Certain pairs of properties, such as position and momentum, cannot both be defined with unlimited precision at the same time. This is not because the electron has a perfectly exact position and momentum hidden away, while humans are simply too awkward to find them. Quantum mechanics says the system itself does not possess those sharp values together in the classical way. The more narrowly a particle's position is defined, the less narrowly its momentum can be defined, and the reverse is also true. Reality at this scale is not blurry because the microscope needs a wipe. It is structured differently. Together, these ideas transformed physics. Wave-particle duality showed that light and matter defy simple categories. De Broglie's matter waves connected particles with wavelength and interference. The double slit experiment revealed that individual quantum events can build up wave-like patterns. Schrödinger's wave function gave physicists a way to calculate probabilities with extraordinary success. Heisenberg's uncertainty principle showed that the limits of quantum description are not merely practical, but built into nature. Early quantum mechanics became one of the great successes of science. It explained atomic structure, chemical bonds, spectra, the behaviour of electrons in materials, and the foundations of much of modern technology. Without it, there would be no proper understanding of semiconductors, lasers, magnetic resonance imaging, or the chemistry that allows ordinary matter to hold together. Yet this was still not the final form of the story. Early quantum mechanics worked beautifully for many problems, especially when dealing with particles moving much slower than light, and when the number of particles stayed fixed. But the deeper universe is not always so tidy. Particles can be created, particles can be destroyed, matter can turn into radiation. High-energy collisions can produce new particles that were not present before, and any truly fundamental theory had to respect Albert Einstein's special relativity, with its strict cosmic speed limit. So quantum mechanics gave physics the strange new rules of matter, but it didn't yet provide the full framework needed for fields, relativity and particle creation all at once. It showed that matter was not made of simple little beads following definite paths. It revealed a world of wave functions, probabilities, interference, uncertainty, and discrete energy states. The universe had become less like a clockwork machine, and more like a quiet mathematical sea of possibilities, where definite events still happen, but not from the kind of underlying certainty classical physics once imagined. Quantum field theory would not erase these discoveries, it would build on them, carrying their strangeness into the fields themselves. Ordinary quantum mechanics is one of the most successful ideas ever made by human beings. That's worth saying gently, because it can be easy to treat it as only a stepping stone, as if it were a slightly awkward draft before the real theory arrived. But early quantum mechanics explained atoms, spectra, chemical bonding, electron behaviour, and the basic stability of matter with astonishing power. It helped make sense of why the material world does not simply collapse into itself, why elements have different properties, and why light comes from atoms in particular colours rather than in one continuous blur. For many situations it works beautifully. An electron in a hydrogen atom can be described using quantum states. Molecules can be understood through shared electron behavior. Materials can be explained through bands of allowed energies. The world of chemistry, electronics, lasers, and modern imaging all rests on quantum mechanics, doing its job with almost unreasonable success. But a theory can be successful and still incomplete. The problem was not that ordinary quantum mechanics suddenly failed at everything. It was that it had been built, in its early form, for a certain kind of situation. Usually it described a fixed number of particles, one electron in an atom, two particles interacting, a system whose ingredients were already there, moving according to quantum rules. That works well for many low-energy problems where particles are not being created or destroyed. But the deeper universe is not always so polite. At high enough energies, particles can appear, particles can vanish, matter can become radiation. Radiation can become matter. A collision between particles can produce new particles that were not present before. In radioactive processes, unstable particles can decay into other particles. In the hot early universe, creation and annihilation were not rare little surprises. They were part of the normal behavior of matter and radiation. Ordinary quantum mechanics was not naturally built for this. It could describe particles, but it struggled when the number of particles itself became changeable. A deeper framework had to let particles appear and disappear, while still preserving the great accounting rules of physics: conservation of energy, conservation of momentum, conservation of electric charge, and other conserved quantities. Nature may be strange, but it is not careless with its bookkeeping. The other major pressure came from Albert Einstein's special relativity. Special relativity says that the speed of light in a vacuum is not merely the speed of one particular object. It is the maximum speed at which usable information or causal influence can travel. No signal can be sent faster than light. Cause and effect must respect that limit. This created a serious challenge. Quantum mechanics had to work with relativity, not merely sit beside it in a different room pretending not to notice. A theory of particles moving near light speed could not allow instant influences or ignore the relationship between energy, momentum, space, and time. If physics wanted to describe electrons at high speeds, particle collisions, radiation, and nuclear processes accurately, quantum theory had to become relativistic. Paul Dirac made one of the boldest moves in this direction. In 1928, he developed a relativistic equation for the electron. It combined quantum mechanics with special relativity in a way that described the electron's spin naturally and gave a much deeper account of its behavior. But the equation also contained something startling. It seemed to imply the existence of states connected to a particle like the electron, but with opposite electric charge. This led toward the prediction of antimatter. Antimatter sounds like something invented by science fiction after too much coffee, but it is entirely real. For the electron, the corresponding antimatter particle is the positron. It has the same mass as the electron, but a positive electric charge rather than a negative one. The prediction was extraordinary because it suggested that the mathematics was not merely describing known particles. It was pointing towards something nature had not yet revealed directly. Then, in 1932, Carl Anderson observed the positron in cosmic ray experiments. A particle track in a cloud chamber curved in the way expected for a positively charged particle with the electron's mass. The positron was real. Dirac's strange relativistic quantum theory had led to a genuine discovery. This changed the mood of physics. Antimatter was not a decorative addition to the particle zoo. It showed that a successful relativistic quantum theory had to allow a richer world than fixed particles following quantum rules. It had to account for particles and antiparticles, for creation and annihilation, for transformations where energy could become matter and matter could become energy, always within the limits set by conservation laws. This is where the language of fields became more than helpful, it became necessary. A field spread through space can have excitations. Those excitations can be counted as particles. If the field gains enough energy in the right way, new excitations can appear. If excitations interact, they can disappear into other forms of energy or produce different excitations in other fields. Particle creation and annihilation make far more sense when particles are not treated as permanent little beads, but as events or ripples in underlying quantum fields. This does not mean ordinary quantum mechanics was wrong. It was and remains one of the greatest working tools in science. But it was not enough for the full high-energy world. It could explain the structure of atoms, but not the complete relativistic theatre in which particles may be born, decay, collide, transform, and vanish. Quantum field theory emerged because nature demanded a theory with more room inside it. It had to keep the successes of quantum mechanics. It had to respect Einstein's speed limit. It had to allow particles and antiparticles. It had to describe changing particle number without breaking conservation laws. And it had to explain why experiments at high energies revealed not a small set of permanent ingredients, but a restless world where fields could exchange energy in discrete, detectable ways. The deeper lesson is calm but profound. The particle is not always a permanent object travelling through a fixed background. Sometimes it is a temporary expression of a field, appearing when the field is excited, disappearing when energy is transferred elsewhere. The universe was not asking physicists to add a complication for elegance. It was showing them that the old framework, brilliant as it was, could not hold all of reality. A quantum field is one of those ideas that sounds impossibly abstract at first, and then slowly becomes one of the most natural ways to picture the deep universe. It begins with the ordinary idea of a field, something spread through space with a value at each place. But it adds the strange rules of quantum mechanics. A quantum field is a field that exists throughout space and behaves quantum mechanically, meaning its excitations come in discrete units. Those discrete units are what are usually called particles. This is the central shift. A particle is not best imagined as a tiny bead sitting on top of a field, like a marble resting on a blanket. It is not a little solid speck being carried along by an invisible substance. In quantum field theory, a particle is a localized excitation of a field. It is a quantum of that field, a small detectable amount of field activity that appears in experiments as something particle-like. The word localized matters, because when a detector records a particle, it records something specific, a click, a track, a flash of energy, a point where an interaction happened. The event is local. It happens here rather than everywhere. But the field behind that event is not limited to that one place. The field is spread throughout space. The particle is the moment when that field shows up in a countable, measurable way. For each type of fundamental particle, modern physics associates a corresponding field. There is an electron field. Every electron in the universe is understood as an excitation of that same electron field. There is a photon field, or more precisely the quantum version of the electromagnetic field. Photons, the quanta of light, are excitations of that field. There are quark fields, whose excitations are quarks. There are neutrino fields, connected to the ghostly particles that pass through matter with remarkable ease. There are gluon fields, involved in the strong nuclear force. There is the Higgs field, which is connected to how many fundamental particles acquire mass. This means the universe is not filled with countless separate electron substances, one for each electron, as if nature were keeping a drawer of tiny identical objects. Instead, all electrons are excitations of the electron field. They are identical because they arise from the same underlying field, following the same rules. This is one reason quantum field theory is so powerful. It explains why fundamental particles of the same type are truly identical, not merely very similar. A useful comparison is a ripple on a pond. The pond is spread out, and a ripple is a local disturbance in it. The ripple can move, carry energy, interact with other ripples, and fade away. In a loose sense, a particle is like a ripple in a field. Another comparison is a vibration on a string. The string can vibrate in certain patterns, and those patterns can carry energy. Or imagine a fabric that can flex, tremble, and form small disturbances moving across it. These images help, but they must be handled carefully. A quantum field is not literally a pond, a string, or a fabric floating inside space. There is no hidden watery substance sloshing beneath reality. There is no cosmic bedsheet being gently shaken by an enormous invisible hand, which is probably for the best. Quantum fields are not ordinary materials filling space like air, fog, or syrup. They are mathematical and physical entities whose behavior is known through their effects. The particles detected, the forces measured, the energies transferred, and the patterns predicted by experiment. This is where quantum fields become difficult to picture, but not impossible to understand. A classical field, like the electromagnetic field in Maxwell's theory, can vary smoothly. A quantum field also has field values and patterns, but its measurable excitations come in discrete units. The electromagnetic field, when treated quantum mechanically, gives rise to photons. Light can spread as a wave, but when it is absorbed or emitted, it does so in individual quanta. The field is continuous in its reach, yet quantum in its behavior. The same basic idea applies to matter. The electron field extends through space, but an electron is detected as a particle-like event. The quark fields extend through space, but quarks appear as excitations bound inside particles such as protons and neutrons. Neutrino fields extend through space, while neutrinos are their faintly interacting excitations. The field is the deeper framework. The particle is how that framework becomes countable. This can feel backwards because ordinary experience begins with objects. A chair looks like a thing. A planet looks like a thing. A grain of dust looks like a very small thing, though still large enough to be annoying on a camera lens. From that perspective, fields seem like an extra layer added later. But in quantum field theory, fields are not decoration around objects. They are the basic ingredients from which particle-like objects emerge. Even emptiness changes meaning. In everyday language, a vacuum means a region with no air or matter in it. In quantum field theory, the vacuum is not absolute nothingness. It is the lowest energy state of the fields. That means a region of space can have no detectable particles and still not be a philosophical void. The fields are still there, but they are in their quietest possible state. This quietest state is not simple in the ordinary sense. Quantum fields have constraints and properties even when no particle is present. The vacuum is not like a blank page before anything has been written. It is more like the calm surface of a deep system with rules already in place. No visible ripple may be passing across it, but the capacity for ripples belongs to it. A quantum field, then, is not a thing in the everyday object-like sense. It is a spread-out physical reality, described with mathematics, tested through experiments, and revealed through the particles and interactions it produces. It fills space not as a substance, but as a set of possible behaviors. When it is excited in the right way, a particle appears. When it settles back down, the particle may be gone, but the field remains. This is the core idea behind quantum field theory. The world is not built first from tiny permanent beads. It is built from fields whose excitations behave as particles. Matter, light, and many of the forces of nature arise from this deeper field structure. So the familiar world is still there. The table remains solid. The lamp still gives off light. The air still carries sound. But underneath those ordinary scenes, quantum field theory suggests a stranger foundation. Fields everywhere, usually quiet, sometimes excited, and capable of producing the particles that make reality visible, touchable, and bright. Empty space sounds like the simplest thing imaginable. Take away the planets, the dust, the gas, the light, the drifting particles, and surely what remains is nothing. A perfect blank. A silent absence. The universe with the furniture removed. Quantum field theory is not quite so generous. In this theory, a vacuum does not mean absolute nothingness. It means the lowest energy state of the quantum fields. That distinction matters. If every field is in its quietest possible condition and no particles are present to be detected, there is still a physical state there. The fields have not vanished. The rules have not vanished. Space is not an empty container with nothing at all inside it. It is a place where quantum fields remain, even when they are not excited enough to produce ordinary particles. This is one of the most important shifts in modern physics. A physical vacuum is not the same thing as philosophical nothingness. Philosophical nothingness would mean no space, no time, no fields, no laws, no possibilities, no stage on which anything could happen. The quantum vacuum is very different. It belongs to a universe that already has space, time, quantum fields, and physical laws. It is not nothing. It is the quietest available state of something. That quietness is still not perfectly still. Quantum fields can have temporary variations in their values, often called vacuum fluctuations. This phrase is easy to exaggerate, so it needs to be handled carefully. It is sometimes described as particles constantly popping in and out of existence in empty space, as though tiny, fully formed objects are appearing everywhere like an overexcited magic trick. That image can be useful as a rough shortcut, but it can also mislead. Vacuum fluctuations are better understood as temporary variations in the behavior of quantum fields, not necessarily as little ordinary particles briefly becoming real in the same way as a particle detected in an experiment. The key point is gentler and stranger. Even when a field is in its lowest energy state, quantum mechanics does not allow it to behave like a perfectly motionless classical object. The vacuum still has structure. It still has measurable consequences. It is quiet, but not blank. One real phenomenon often associated with quantum vacuum behavior is the Casimir effect, named after the Dutch physicist Hendrik Casimir. In a simplified version, imagine two very thin conducting plates placed extremely close together in a vacuum. The presence of the plates changes which electromagnetic field modes can exist between them compared with outside them. This difference can produce a tiny attractive force between the plates. The force is small, and it only becomes significant at very short distances, but it has been measured. That matters because it shows that what appears to be empty space can still be affected by the allowed behavior of quantum fields. The vacuum is not simply a dead absence. It has constraints, and under the right conditions those constraints can show up as physical effects. Empty space, it turns out, can still be fussy about boundaries. Another important clue came from the Lamb shift, named after Willis Lamb. In the 1940s, careful measurements of hydrogen showed that certain energy levels were slightly different from what the earlier Dirac theory predicted. The shift was tiny, but real. Quantum electrodynamics, the quantum field theory of electromagnetism, explained it by taking into account interactions between the electron, the electromagnetic field, and the quantum vacuum. This was a crucial success. It showed that quantum fields do not merely affect exotic particle collisions in enormous machines. They also influence the fine details of atoms. The simplest atom, hydrogen, became a place where the subtle structure of the vacuum could leave a measurable signature. The effect was not dramatic in everyday terms. No table began floating away in protest. But scientifically it was profound. The Casimir effect and the Lamb shift both point toward the same deeper lesson. The absence of ordinary particles is not the absence of physical structure. Quantum field theory describes empty space as a state with properties. Those properties can influence forces, energy levels, and measurable outcomes. The vacuum may look empty to the eye, and to most instruments under everyday conditions, but it is not empty in the deepest field-theoretic sense. This also helps explain why ordinary language struggles here. The word empty usually means that something has been removed. An empty cup contains no tea. An empty room contains no people. An empty road contains no traffic, which is often when someone decides to start roadworks, just to keep the universe humble. But in physics, an empty region can still contain fields in their lowest energy state. The emptiness is relative to particles and matter, not relative to existence itself. There is also a difference between ordinary empty space and a carefully defined physical vacuum. Outer space, for example, is often called a vacuum, but it is not perfectly empty. It contains sparse gas, dust, radiation, cosmic rays, neutrinos, magnetic fields, and the faint glow of the cosmic microwave background. Even the emptiest known regions between galaxies are not absolute nothingness. They are simply far emptier than anything naturally found on Earth. A laboratory vacuum is also not absolute nothing. It is a region where as much matter as possible has been removed, while space, fields, and physical laws remain. The quantum vacuum is a more precise idea. It is the lowest energy state available to the fields in a given situation. That phrase may sound modest, but it carries a great deal. It means the vacuum can depend on the fields, boundaries, and conditions involved. It means there can be structure without particles, and physical behavior without visible material. It means that the universe at its deepest levels is not well described as objects sitting in a blank void. This does not mean the vacuum is a source of unlimited energy, or a place where anything can happen without rules. Quantum field theory is not a permission slip for fantasy. Vacuum behavior is constrained, mathematical, and measurable. The effects are subtle. They appear in precise experiments, atomic energy shifts, and calculations that have to be handled carefully. The vacuum is strange, but it is not a cosmic vending machine for miracles. Still, the idea remains quietly astonishing. Remove every obvious particle from a region, and quantum field theory does not leave pure nothingness behind. It leaves fields in their lowest energy state. It leaves constraints. It leaves the possibility of fluctuations. It leaves the hidden structure that allows particles, forces, and interactions to make sense when energy is present. So empty space is not empty in the deepest physical sense. It is more like a calm sea on a windless night. From a distance, it may look perfectly smooth and inactive, but the sea is still there. Its depth is still there. Its rules are still there. And under the right conditions, even the quietest surface can reveal that it was never truly blank. A universe made of fields would still be strangely quiet if the fields never interacted. There could be excitations, particles, ripples of matter and light, but nothing would bind, transform, shine, decay, or build anything more interesting than a very lonely collection of disturbances. The world becomes rich because fields do not merely exist beside one another, they influence one another. In everyday language, a force often sounds like a push or pull between objects. A hand pushes a door. A magnet pulls on a paperclip. Earth pulls a dropped object downward. It is easy to imagine invisible strings stretching between things, tugging them across space. That picture can be useful at ordinary scales, but quantum field theory describes forces in a deeper way. Forces are not mysterious threads reaching across a void. They are interactions between fields. This means that when an electron responds to electromagnetic force, it is not being tugged by a tiny unseen rope. The electron field interacts with the electromagnetic field. The visible result may look like attraction, repulsion, radiation, scattering, or absorption, depending on the situation. What appears as a force is really field behavior playing out according to precise rules. In quantum field theory, the fields associated with forces also have quanta. These are often called force-carrying particles, though the phrase should be used carefully. For electromagnetism, the quantum of the electromagnetic field is the photon. Photons are involved in electromagnetic interactions, including light, radio waves, and the forces between electrically charged particles. For the strong nuclear force, the relevant force carriers are gluons. Gluons are connected to the field that binds quarks together inside protons and neutrons. For the weak nuclear force, the carriers are the W bosons and Z bosons, which are involved in certain kinds of particle transformation. These force carriers are not all the same kind of thing doing the same kind of job in different uniforms. The photon is massless and can mediate a long-range force. Gluons carry the strong force, but because of the peculiar nature of that force, they're confined within particles such as protons and neutrons under ordinary conditions. The W and Z bosons are massive, which is one reason the weak force acts over an extremely short range. The details differ, but the broader field idea remains. Interactions are described through fields and their quanta. There is one phrase that often causes confusion here: virtual particles. In popular explanations, forces are sometimes described as particles throwing other particles back and forth, like a slightly chaotic game of subatomic catch. This can be a useful first image, but it can easily become too literal. Virtual particles in quantum field theory are not ordinary particles, briefly becoming real, in the same way as detectable particles in an experiment. They're calculation tools that appear inside the mathematical method used to describe interactions. They help physicists calculate probabilities, but they should not be imagined as tiny, fully formed objects secretly darting around with little schedules to keep. The electromagnetic interaction is the most familiar place to begin. Electrons carry electric charge, so the electron field interacts with the electromagnetic field. This interaction is responsible for an enormous amount of the familiar world. It shapes atoms because negatively charged electrons are bound to positively charged atomic nuclei. It shapes chemistry because chemical bonds depend on how electrons arrange themselves and interact. It explains why matter resists being pushed through other matter, since the electron structures of atoms respond electromagnetically when they are brought close together. That resistance is part of why a table feels solid. The atoms in a hand do not simply pass through the atoms in the table, because the electromagnetic interaction, together with quantum rules for electrons, creates stable structures and strong resistance at close range. Solidity is not caused by tiny hard spheres touching like billiard balls. It is field interaction made familiar. The everyday firmness of the world is electromagnetism and quantum mechanics, wearing very convincing ordinary clothes. Light also belongs to this same field story. A photon is an excitation of the electromagnetic field, and when light is emitted or absorbed, the electromagnetic field is interacting with charged matter. An atom can absorb a photon and move into a higher energy state. It can emit a photon and drop into a lower energy state. A radio antenna works because moving charges interact with the electromagnetic field, producing waves that travel outward. A glowing lamp, a reflected face in a mirror, a blue sky, and the signal from a wireless router all belong to the same deep family of electromagnetic field behavior. The router, admittedly, expresses this grand unity by occasionally needing to be turned off and on again. The strong nuclear force is less visible in daily life, but it is essential for matter. Protons and neutrons are not elementary particles in the same way electrons appear to be. They are made of quarks. Quarks interact through gluon fields, and this interaction is described by quantum chromodynamics. The strong force binds quarks together so tightly that isolated quarks are not found under ordinary conditions. They are confined inside composite particles such as protons and neutrons. Gluons are unusual because they themselves carry the kind of charge involved in the strong interaction, known as colour charge. This is not visual colour. It has nothing to do with red paint, blue light, or whether a quark is tastefully decorated. It is the name physicists use for a quantum property that determines how quarks and gluons interact. Because gluons carry colour charge, they interact with one another as well as with quarks, making the strong force far more complex than electromagnetism. This strong interaction does more than hold quarks together. It also provides much of the mass of ordinary matter. The individual quarks inside protons and neutrons contribute only a small fraction of their total mass. Most of the mass comes from the energy of the strong force field and the dynamic motion and confinement of quarks and gluons. In this sense, the weight of the everyday world is not simply the sum of little pieces. It is deeply tied to field energy. The weak nuclear force has a different personality again. It is involved in processes where particles can change identity. One important example is beta decay, where a neutron can transform into a proton while emitting an electron and an antineutrino. At the quark level, this involves one kind of quark changing into another through the weak interaction. The W boson and Z boson are central to this force. The weak interaction is also important in stars. Some nuclear processes that help stars shine depend on weak interactions, especially when protons are converted in ways that allow fusion chains to proceed. Neutrinos, those almost ghost-like particles that pass through matter with remarkable ease, are deeply connected to the weak force. Trillions of neutrinos from the Sun pass through a human body every second, mostly without noticing the body at all. It is one of nature's more humbling social arrangements. Together, these interactions show why quantum field theory is not just a theory of particles sitting in space. It is a theory of behavior, transformation, binding, radiation, and change. Fields can excite other fields. Particles can scatter. Atoms can emit light. Quarks can bind into protons. Neutrons can decay. Stars can shine. Matter can hold together. The central idea is that forces are field interactions made visible through their effects. Sometimes those effects are gentle, like light reflecting from a page. Sometimes they are hidden, like gluons binding quarks deep inside a proton. Sometimes they are transformative, like the weak interaction changing one particle type into another. But in each case, quantum field theory replaces the old image of objects tugging across empty space with something more subtle and powerful. Reality is not just a collection of ingredients, it is a set of fields interacting under rules. The universe has structure because the fields are not isolated. They speak to one another, exchange energy and momentum, and produce the patterns that become matter, light, chemistry, radiation, and stars. In that quiet exchange between fields, the physical world begins to move. Among all the strange ideas in quantum field theory, one of the most successful begins with something familiar. Light interacting with matter. A lamp gives off light. A mirror reflects it. An atom absorbs it. An electron responds to it. A charged particle can emit it. these everyday-looking events are expressions of one deep interaction, the electromagnetic interaction. When this interaction is described using quantum field theory, it is called quantum electrodynamics. Quantum electrodynamics is the quantum field theory of charged particles and photons. It describes how particles such as electrons interact with the electromagnetic field, and how photons, the quanta of that field, are emitted, absorbed, and exchanged in physical processes. It is the field theory behind much of ordinary matter's behaviour: light scattering, electrons shifting in atoms, magnetic effects, radiation, and the subtle details of how charged particles behave. It is also one of the most precisely tested theories in all of science, which is slightly rude of it, considering how strange it looks under the hood. The modern form of quantum electrodynamics emerged through the work of several key physicists. Richard Feynman developed a vivid and powerful way of calculating interactions using diagrams. Julian Schwinger developed a mathematically rigorous approach with extraordinary precision. Shinichiro Tomonaga independently built a relativistic formulation that solved many of the same deep problems. Freeman Dyson then helped show how these different approaches were connected, revealing that they were not competing islands but different paths through the same theoretical landscape. Together, their work transformed a difficult and sometimes troubling theory into a practical engine for prediction. Quantum electrodynamics did not make the microscopic world feel ordinary, but it made the strangeness calculable. The central interaction is simple to say. Charged particles, such as electrons, interact with the electromagnetic field. Photons are the quanta of that field. An electron can emit a photon. An electron can absorb a photon. Two charged particles can influence one another through their interaction with the electromagnetic field. But when physicists try to calculate exactly what can happen, the simplicity quickly blooms into a forest of possibilities. This is where Feynman diagrams became famous. A Feynman diagram is a visual tool for organizing calculations in quantum field theory. It may show lines representing particles, points where interactions occur, and possible ways particles can exchange energy and momentum. But it is important to be precise. These diagrams are not literal snapshots of tiny objects flying through space. They are not little cartoons of what a particle is secretly doing when no one is watching. They are bookkeeping devices for possible interaction terms in the mathematics. That does not make them less powerful. In fact, their power comes from making the calculations manageable. Quantum electrodynamics considers not just one simple route from an initial situation to a final result, but many possible contributions. Some are simple, some are more complicated. The more complicated ones usually contribute smaller corrections, but those tiny corrections can matter in precise measurements. A familiar example involves the electron's magnetic behavior. Electrons have an intrinsic magnetic property connected to their spin. Early theory predicted a particular value for this magnetic behavior, but quantum electrodynamics showed that the value receives tiny corrections because the electron interacts with the quantum electromagnetic field. It is not just a bare little object with a simple magnetic label attached. It is surrounded, in the language of the theory, by interactions with the field that subtly modify its observed properties. The astonishing part is how accurately quantum electrodynamics predicts those modifications. Measurements of the electron's magnetic moment agree with theoretical calculations to an extraordinary number of decimal places. This agreement is often described as one of the greatest precision achievements in science. It is not merely that the theory gets the general idea right. It gets tiny details right, details so small that they require extremely careful experiments and highly refined calculations to compare. This is one reason quantum electrodynamics became such a landmark. It showed that quantum field theory was not only a strange philosophical framework, it could produce numbers that matched nature with breathtaking accuracy. The theory seemed almost too peculiar to be true, and then the measurements kept quietly saying, yes, apparently reality really does work like this. But there was a serious problem hidden inside the early calculations. In some versions of the theory, certain quantities appeared to become infinite. Infinite answers are not especially helpful when trying to describe a real electron in a real laboratory. They are the mathematical equivalent of a machine coughing politely and then producing smoke. Physicists needed a way to deal with these infinities without throwing away the theory's successful predictions. The method that made this possible is called renormalization. Renormalization is often made to sound mysterious, and in fairness, it is not exactly bedtime arithmetic. But the basic idea can be explained calmly. The quantities that appear in the deepest equations are not always the same as the quantities measured in the laboratory. A particle such as an electron is observed together with the effects of its interactions with fields. Renormalization allows physicists to connect the mathematical parameters of the theory to measured physical quantities, absorbing problematic infinities into definitions of things like observed charge and mass. That may sound like hiding mess under a rug, but it is not simply a trick. Renormalization became a precise and systematic method. It showed how predictions could be made at a given scale and compared with experiment. Later, physicists came to understand renormalization even more deeply, as a way of seeing how physical descriptions change with scale. The behavior of a system at one energy level may be described differently from its behavior at another, while still being part of the same underlying framework. In quantum electrodynamics, renormalization turned a theory that seemed threatened by infinities into one of the sharpest predictive tools ever created. It allowed the strange mathematics of fields, photons, charged particles, and virtual processes to produce finite answers that could be tested. The word virtual needs the same caution as before. In quantum electrodynamics calculations, virtual photons can appear inside Feynman diagrams, but these are not ordinary photons briefly existing like tiny flashes of light that could be caught by a small enough camera. They are internal elements of the calculation. They help represent how interactions contribute to measurable outcomes. Treating them too literally can make the theory sound easier at first, but more confusing later. What matters is that the final predictions are real and testable. Quantum electrodynamics explains the scattering of light and electrons. It explains details of atomic energy levels. It explains the Lamb shift, where the energy levels of hydrogen differ slightly from earlier predictions. It explains the subtle magnetic properties of the electron. It gives physicists a way to calculate how charged particles and photons interact with extraordinary precision. This is the quiet lesson of quantum electrodynamics. A theory can be deeply unintuitive and still be scientifically powerful. It can describe nature through fields, quanta, probabilities, diagrams, corrections, and renormalization, and still land on numbers that match experiments better than almost anything else humans have ever measured. There is something rather beautiful about that. The electromagnetic interaction is part of daily life. It is in light, color, chemistry, electricity, magnetism, touch, and the structure of atoms. Yet when followed down to its deepest tested rules, it leads to one of the strangest mathematical frameworks in physics. The ordinary glow of a lamp is connected to a theory that handles photons, electrons, vacuum effects, and microscopic corrections with astonishing care. Quantum electrodynamics shows why quantum field theory earned its place at the center of modern physics. It is not just an abstract way to speak about invisible fields. It works, it predicts, it survives careful measurement. and it reveals that behind even the gentlest beam of light, the universe is carrying out a field interaction of remarkable precision. Symmetry sounds, at first, like a word that belongs to art, architecture, or perhaps a very carefully arranged plate of biscuits. It suggests balance, reflection, and pleasing patterns. A butterfly's wings have symmetry. A snowflake has symmetry. A calm lake can reflect mountains so neatly that the world seems to have been folded in half. In physics, symmetry means something related but deeper. A symmetry is a transformation that leaves the essential laws unchanged. Something can be moved, rotated, shifted, or changed in a certain way, and the underlying rules still work exactly as before. The appearance may alter, but the law remains the same. A simple example is location. If an experiment is performed in one quiet laboratory, then moved to another quiet laboratory across the country, the basic laws of physics do not suddenly change their mind. Electrons do not behave politely in Cambridge and then become theatrical in Edinburgh. The same physical laws apply. That sameness is a kind of symmetry. The laws of nature do not depend on where the experiment is placed. Time gives another example. If the same experiment is performed today and again tomorrow under the same conditions, physics expects the same rules to apply. The result may differ if the conditions differ, of course. A kettle filled with water behaves differently from a kettle filled with soup and raises more questions about the owner. But the basic laws themselves do not change from one day to the next. This symmetry through time is connected to one of the deepest ideas in physics. That connection was revealed by Emmy Noether, one of the most important mathematicians in the history of modern science. In the early 20th century, Noether proved a theorem that linked symmetries with conservation laws. Noether's theorem says, in broad terms, that whenever a physical system has a continuous symmetry, there is a corresponding conserved quantity. This is a beautiful idea because it turns conservation laws into clues. Conservation of energy is linked to symmetry in time. If the laws of physics do not change from moment to moment, energy is conserved. Conservation of momentum is linked to symmetry in space. If the laws do not depend on where something happens, momentum is conserved. Conservation of angular momentum is linked to rotational symmetry. If the laws do not depend on which direction a system is facing, angular momentum is conserved. These conservation laws are not just convenient accounting habits. They are deeply woven into the structure of physical law. Energy, momentum, and angular momentum are not preserved because nature has a tidy personality, although it often seems to. They are preserved because of underlying symmetries. In ordinary life, these symmetries can be easy to miss because the world is full of friction, noise, furniture, weather, and other small acts of complication. But in the cleaner language of physics, they become guiding principles. They help physicists understand which processes can happen, which cannot, and which quantities must balance before and after an interaction. Quantum field theory takes this idea and makes it even more powerful. Some symmetries are visible in ordinary space. A rotating object, a shifted experiment, or a repeating motion can be pictured directly. But quantum field theory also depends on internal symmetries. These are not symmetries of position or direction in everyday space. They are symmetries in the mathematical structure of fields themselves. They may involve transformations of a field that do not look like moving a chair across a room or turning a wheel, but they still leave the underlying physics unchanged. Internal symmetries are crucial for understanding particle behavior. They help explain why certain particle properties are conserved, why particles interact in particular ways, and why the forces of nature have the structures they do. They are hidden from ordinary sight, but they shape what can occur. One of the most important kinds of symmetry in modern field theory is gauge symmetry. The word gauge can sound rather technical, and admittedly it does not arrive carrying a basket of friendliness. but the core idea can be approached gently. A gauge symmetry is a kind of freedom in how a field is described mathematically, where different descriptions represent the same physical situation. The physics must remain unchanged even if the description is adjusted in a particular way. At first, this may sound like a mere matter of notation, as though physicists are just arguing about labels while the universe waits patiently for them to finish. But gauge symmetry turns out to be far more than a choice of words. When physicists require that certain symmetries remain valid not just globally, everywhere at once, but locally, from point to point in space and time, new fields must be introduced to keep the theory consistent. Those fields are associated with forces. This is one of the deepest ideas in quantum field theory. Forces can arise from the requirement that symmetries remain consistent everywhere. Electromagnetism is the simplest and most familiar example. The field theory of electromagnetism can be understood through a gauge symmetry, associated with the electron field. When the theory is required to respect that symmetry locally, the electromagnetic field naturally appears. The photon, as the quantum of that field, is connected to the electromagnetic interaction. The force is not added by hand like an afterthought. It emerges from the structure needed to preserve the symmetry. This same broad idea extends to the nuclear forces. The strong nuclear force described by quantum chromodynamics is built around a gauge symmetry connected to color charge. Color charge is not ordinary color, but a quantum property of quarks and gluons. The structure of this symmetry leads to gluon fields, and those gluon fields govern how quarks are bound inside protons, neutrons, and other particles. The weak nuclear force also fits into a gauge field framework. Along with electromagnetism, it is part of the electroweak theory developed through the work of Sheldon Glashow, Abdus Salem, and Steven Weinberg. In that theory, electromagnetism and the weak interaction are related through a deeper symmetry that becomes hidden or broken at lower energies. This does not mean the symmetry is false. It means the state of the fields makes the forces appear different in the world we usually observe. Symmetry breaking is another important idea. Sometimes the underlying laws have a symmetry, but the actual state of the system does not display it openly. A gentle comparison is a pencil balanced perfectly on its tip. In principle, every direction around it is equal, but when it falls, it chooses one direction. The underlying situation was symmetric, but the final state is not. In quantum field theory, forms of symmetry breaking help explain why certain particles and forces behave as they do. This is especially important for the Higgs field, though the full story belongs to a later part of the journey. The essential point here is that hidden order does not always look orderly at first glance. The world of particles can seem crowded and complicated, with electrons, quarks, photons, gluons, neutrinos, and bosons, all behaving according to unfamiliar rules. Yet beneath that apparent complexity, physicists find patterns of symmetry. Those patterns are not decorative. They decide the architecture of the theory. They shape which fields exist, how particles interact, which quantities are conserved, and which transformations are allowed. A conservation law becomes not just a fact to memorize, but a trace left behind by symmetry. A force becomes not just a push or pull, but a consequence of keeping a field theory consistent. This is why symmetry is one of the quiet master keys of modern physics. It does not make quantum field theory simple exactly. Nothing that includes gluons, renormalization, and invisible internal transformations can honestly be accused of being simple. But symmetry makes the theory intelligible. It reveals that the strange rules are not random. They are constrained by deep structure. The universe, at the level of quantum fields, may look restless and unpredictable in individual events. Particles scatter, photons are emitted, quarks bind, neutrinos slip away almost unnoticed. But beneath the motion, there is order. Some quantities remain conserved. Some transformations leave the laws unchanged. Some hidden symmetries demand the existence of fields that become forces. Quantum field theory is therefore not only a theory of particles and interactions, it is a theory of patterns that survive change. It shows that behind the visible behavior of matter lies a quieter architecture, one where symmetry and conservation are tied together. The world is not merely a crowd of tiny events. It is a field of possibilities governed by hidden order, and that order is one of the reasons the universe can be strange without being chaotic. This standard model is not a single little equation sitting neatly on a shelf, waiting to explain the universe with suspicious elegance. It is better understood as a carefully built framework, a collection of quantum field theories that describes the known fundamental particles and 3 of the 4 fundamental interactions. It is one of the great achievements of modern physics, not because it answers every question, but because it explains so much with such remarkable precision. At its heart, the standard model is a field theory. It does not begin by imagining a universe made from tiny permanent beads drifting through empty space. Instead, it describes a set of fields, each spread through space, each with its own rules, and each capable of producing the particles detected in experiments. The particles are the excitations, the fields are the deeper structure. The standard model describes the electromagnetic interaction, the strong nuclear interaction, and the weak nuclear interaction. Gravity is not included in the same successful quantum field theory framework. That absence matters, and it remains one of the great open problems in physics. But for the particles and forces it does describe, the standard model has been tested again and again in particle accelerators, atomic measurements, scattering experiments, and observations of radioactive decay. The particles of the standard model are usually grouped into matter particles and force-related particles. The matter particles are quarks and leptons. The force-related particles are gauge bosons. The Higgs boson stands in a special place connected to the Higgs field and to the way many fundamental particles acquire mass. Quarks are among the basic matter fields. They come in several types, usually called flavors. The up quark and down quark are the most familiar in ordinary matter because they are the main quarks found inside protons and neutrons. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. These quarks are bound together by the strong nuclear force through gluon fields. There are heavier relatives too. The charm quark, strange quark, top quark, and bottom quark. These do not normally appear as stable ingredients in everyday objects, but they are produced in high-energy environments such as particle collisions. They are not just extra names added to make physics students sigh gently into their notebooks. They are real excitations of quark fields, observed through their behavior and decay products. Leptons form another family of matter fields. The electron is the most familiar lepton. Electrons surround atomic nuclei and shape chemistry, electricity, magnetism, and the structure of ordinary matter. Without the electron field and its excitations, atoms would not form in the way they do. Molecules would not hold together, and cups of tea would have a serious structural problem. The electron also has heavier relatives, called the muon and the tau particle. These are similar to the electron in some ways, but much more massive and unstable. They appear in high-energy processes and decay into lighter particles. Alongside these charged leptons are neutrinos, the electron neutrino, muon neutrino, and tau neutrino. Neutrinos are extremely light and interact through the weak force, allowing them to pass through matter with extraordinary ease. Vast numbers of neutrinos from the Sun pass through Earth every second, almost as though the planet is barely there, which is a humbling arrangement for a planet with such confidence in its own solidity. The gauge bosons are connected to interactions. The photon is the quantum of the electromagnetic field. It is involved whenever charged particles interact electromagnetically, and it is also the particle of light. Photons connect the field theory of electromagnetism to everyday experiences such as colour, reflection, heat radiation, radio waves, and the light from stars. Gluons are the gauge bosons of the strong nuclear force. They bind quarks together inside protons, neutrons, and other particles made of quarks. Gluons are unusual because they carry colour charge themselves, meaning they interact with one another as well as with quarks. This self-interaction helps make the strong force very different from electromagnetism. It also contributes to confinement, the fact that quarks are not found isolated under ordinary conditions. The W bosons and Z boson are the gauge bosons of the weak nuclear force. The weak interaction is responsible for certain particle transformations, such as beta decay. It can allow one kind of quark to change into another. It is also deeply involved with neutrinos and with nuclear processes inside stars. Unlike the photon, the W and Z bosons are massive, which helps explain why the weak force acts only over an extremely short range. The story becomes even more elegant with electroweak theory. Sheldon Glashow, Abdus Salam, and Steven Weinberg helped show that electromagnetism and the weak interaction are not completely separate at a deeper level. At high energies, they can be understood as parts of a unified electroweak framework. At lower energies, the symmetry of this framework is hidden or broken, so the two interactions appear very different in the world of atoms, light, and radioactive decay. This is where the Standard Model shows the power of symmetry. The interactions are not chosen at random. They are built from gauge symmetries, internal symmetries that guide the form of the field theories. Those symmetries help determine which gauge bosons exist, how fields interact, and what kinds of processes are allowed. This Standard Model may look like a catalogue of particles at first glance, but underneath it is a carefully constrained structure of fields and symmetries. Then there is the Higgs field. The Higgs field is present throughout space, and its interaction with many fundamental particles is connected to their masses. The Higgs boson is the quantum excitation of that field. It is not the same thing as the field itself. This distinction is important. The field is the underlying presence. The boson is the detectable ripple. The discovery of the Higgs boson in 2012 at the Large Hadron Collider was one of the defining experimental confirmations of the Standard Model. The discovery was announced by the ATLAS and CMS collaborations at CERN, the European Organisation for Nuclear Research, one of the world's major centres for particle physics. CERN operates the Large Hadron Collider near Geneva, where protons are accelerated around a ring roughly 27 kilometres in circumference and collided at enormous energies. From those collisions, physicists reconstruct what happened by studying sprays of particles, energy deposits, decay patterns, and statistical signatures. This is a crucial point. The Standard Model is not just an elegant chart. It is a working scientific theory tested by experiments. Detectors do not look directly at fields in the way a camera photographs a tree. Instead, they measure the consequences of fields, particles created in collisions, tracks through detector layers, flashes of light, deposited energy, and the probabilities of different outcomes. From these clues, physicists test whether the field theory matches nature. And again, it has. The Standard Model is not complete. It does not explain gravity as a quantum field theory in the same successful way. It does not identify dark matter. It does not explain dark energy. It does not fully explain why neutrinos have mass, or why the universe contains much more matter than antimatter. It has many measured ingredients whose values are not derived from a deeper known principle. In that sense, it is not the final book of reality, but it is still extraordinary. It places quarks, leptons, gauge bosons, and the Higgs boson into one coherent field-based framework. It explains how the electromagnetic strong and weak interactions operate. It connects symmetry to force, fields to particles, and experiment to mathematics. It shows that the visible world is not merely assembled from little objects, but from excitations of underlying fields obeying precise rules. The standard model is where quantum field theory becomes the working map of the subatomic world. It is not merely a philosophical idea about invisible fields beneath reality. It is the structure physicists use to describe what matter is made of, how particles interact, how they transform, and why the universe at small scales behaves with such strange and consistent order. The Higgs field is one of the most famous ideas in modern physics, partly because it sounds almost mythical. A field spread throughout the universe, quietly shaping the masses of fundamental particles, waiting in the background of every atom, every star, every hand, every breath. It has the kind of name that feels as though it should come with dramatic music and a very serious narrator standing beside a particle accelerator. But the real story is subtler and better. The Higgs field is a quantum field present throughout space. In the standard model, it is connected to how many fundamental particles acquire mass. That does not mean it is a sticky substance dragging on particles as they move, like honey spread across the universe. It also does not mean it creates all mass in every possible sense. The truth is more precise. Many fundamental particles gain their rest mass through their interaction with the Higgs field. The stronger a particle's interaction with the Higgs field, the greater its associated mass tends to be. This is a strange idea because mass feels so basic. It seems as though every object simply has it. A stone has mass. A planet has mass. A sleepy cat on a sofa has mass and may use it strategically to prevent anyone else from sitting down. But at the level of fundamental particles, mass is not merely an obvious built-in label. It is tied to the structure of fields and symmetries. To understand why the Higgs field matters, it helps to return to symmetry. The standard model is built around deep gauge symmetries. These symmetries help determine the interactions between fields. But there was a problem. The equations describing the electroweak theory worked beautifully when the force-carrying particles were massless. Yet in the real world, the W bosons and Z boson are massive, while the photon is massless. Something had to explain how the theory could keep its underlying structure while allowing some particles to have mass. The answer came through what is called spontaneous symmetry breaking. The phrase sounds rather dramatic, as though symmetry has had a difficult morning. But the basic idea can be made gentle. Sometimes the laws of a system have a symmetry, but the state the system settles into does not display that symmetry openly. Imagine a perfectly round hill, with a small ball balanced at the top. Every direction down the hill is equally possible. The setup is symmetric. But once the ball rolls, it chooses one direction. The symmetry of the situation is still present in the underlying setup, yet the actual state has selected a particular outcome. The Higgs field is often explained with comparisons like this because it has a non-zero value even in empty space. Instead of settling at zero, the field settles into a background state that fills the universe. This state changes the behavior of particles moving through it. The symmetry is not destroyed in a careless way. Rather, it is hidden by the state the field occupies. The result is that particles can acquire mass while the deeper theory remains mathematically consistent. In the 1960s, several physicists developed this mechanism in related forms. Peter Higgs, François Engler, Robert Brute, Gerald Guralnick, Carl Hagen, and Tom Kibble were among the scientists connected to the theoretical development of what is now called the Higgs mechanism. Their work showed how a field could give mass to certain particles without wrecking the gauge structure of the theory. It was not a small patch added to cover an embarrassment. It became a central part of the standard model. The Higgs field affects different particles differently. The electron interacts with it and has a small but non-zero mass. The top quark interacts with it very strongly and is far more massive. The photon does not acquire mass through the Higgs field, which is why electromagnetism has a long range and light can travel across cosmic distances. The W bosons and Z boson do acquire mass, which is one reason the weak nuclear force acts only over extremely tiny distances. This helps explain why the weak force seems weak at ordinary scales, even though it is essential to the universe. A force carried by massive particles is short-ranged, because those particles cannot mediate interactions over long distances in the way a massless photon can for electromagnetism. The Higgs field, then, is not just an isolated curiosity. It helps shape the different personalities of the forces themselves. Then there is the Higgs boson. The Higgs boson is not the Higgs field. This is one of the most important distinctions. The field is the thing spread throughout space. The boson is a quantum excitation of that field, a detectable ripple, a particle-like event that can be produced under the right conditions. Calling the Higgs boson the Higgs field would be a little like calling one ripple the entire pond. The ripple tells you the pond is there, but it is not the whole pond. For decades, the Higgs boson was the missing piece needed to confirm that the Higgs field was not just a beautiful theoretical idea. Physicists expected that if the field existed, then under extremely high energy conditions, an excitation of it should be produced. Finding it would require enormous machines, extraordinary detectors, and a level of patience usually associated with mountains and people waiting for software updates. That search culminated at the Large Hadron Collider at CERN, the European Organization for Nuclear Research near Geneva. The Large Hadron Collider accelerates protons around a circular tunnel roughly 27 kilometers in circumference and smashes them together at immense energies. These collisions briefly concentrate enough energy into tiny regions of space to produce heavy, short-lived particles that do not appear under ordinary conditions. In 2012, the ATLAS and CMS collaborations at the Large Hadron Collider announced the discovery of a new particle consistent with the Higgs boson. It was not seen directly like a little glowing bead in a photograph. It appeared through the patterns of particles into which it decayed, the statistical evidence gathered from countless collision events, and the careful comparison between theory and measurement. The discovery was a major confirmation of the Standard Model and one of the landmark achievements of modern experimental physics. The Higgs boson's discovery mattered because it confirmed that the Higgs field has physical reality. The field was not merely an elegant line in the theory. Its excitation could be produced and detected through its decay signatures. The invisible field had left a visible trail in the data. But the Higgs field is often misunderstood. It is sometimes described as the source of all mass. That is not quite right. The Higgs field gives mass to many fundamental particles, such as electrons, quarks, and the W and Z bosons. But most of the mass of ordinary matter does not come directly from the Higgs field. A proton, for example, is made of quarks, but the individual quark masses account for only a small part of the proton's total mass. Most of the proton's mass comes from the energy of the strong nuclear force, the dynamic motion of quarks, the energy stored in gluon fields, and the effects of confinement inside the proton. The same is true for neutrons. Since atoms get most of their mass from protons and neutrons, most everyday mass comes from strong force energy, rather than directly from the Higgs field. This makes the story more interesting, not less. The Higgs field helps explain why certain fundamental particles have rest mass at all. The strong force explains why most ordinary matter is as massive as it is. Reality is not usually powered by one neat answer. It prefers layered answers, the kind that make a simple question look back at you and quietly grow several extra rooms. The Higgs field is therefore not a magical mass fluid. It is a specific quantum field with a non-zero background value, tied to spontaneous symmetry breaking and the structure of the electroweak theory. It helps explain why the W and Z bosons are massive while the photon is not. It gives mass to many elementary particles. Its quantum excitation, the Higgs boson, was discovered at CERN in 2012. And beneath all of that is the wider lesson of quantum field theory. Properties that seem basic, like mass, may arise from interactions with fields. The things that make matter behave the way it does are not always little objects hidden inside other little objects. Sometimes they are conditions of space itself, quiet fields spread everywhere, shaping what particles can be. The solid world feels immediate and simple, but part of its deep structure depends on a field that fills the universe, settled into a state that changes the behavior of fundamental particles. The Higgs field does not explain everything about mass, and it does not complete physics. But it shows how profoundly field-based reality can be. Even the heaviness of matter, one of the most ordinary facts of experience, carries the imprint of invisible quantum fields. The Higgs field explains something essential about mass, but it does not explain the whole weight of the ordinary world. That is one of the quiet surprises of modern physics. The field famous for giving mass to many fundamental particles is not by itself the main reason a stone feels heavy, a planet holds itself together, or a human body has weight when standing on bathroom scales that are clearly being rather dramatic. Most of the mass of familiar matter comes from somewhere else. To see why, the story has to move inside protons and neutrons. These are the particles that make up atomic nuclei, and atomic nuclei contain almost all the mass of ordinary atoms. Electrons are important for chemistry, electricity, and the size of atoms, but they are extremely light compared with protons and neutrons. So if the everyday world has mass, much of the answer lies inside the nucleus. Protons and neutrons are not elementary particles. They are made of quarks, held together by the strong nuclear force. The quantum field theory that describes this force is called quantum chromodynamics. It is the theory of quarks and gluons, and it is one of the central parts of the Standard Model, where quantum electrodynamics describes the electromagnetic interaction between charged particles and photons. Quantum chromodynamics describes the strong interaction between quarks and gluons. The name sounds oddly colourful, and that is not an accident. In quantum chromodynamics, quarks carry a property called colour charge. This is not ordinary visual colour. A quark is not literally red, green, or blue, and no tiny artist has been let loose inside the proton with a paintbrush. Colour is a naming convention for a quantum property, similar in spirit to electric charge, but belonging to the strong interaction. Gluons also carry colour charge, which makes the strong force far more complex than electromagnetism. That difference matters. Photons, the quanta of the electromagnetic field, do not carry electric charge. Because of that, photons do not directly interact with other photons under ordinary conditions. Gluons, by contrast, do carry colour charge, so they interact with quarks and with other gluons. The force carriers of the strong force are themselves strongly involved in the force. It's a little like having messengers who not only deliver the message, but also argue energetically with each other on the way. This self-interaction helps produce one of the strangest features of quantum chromodynamics: confinement. Quarks are not found alone under ordinary conditions. They are confined inside composite particles such as protons, neutrons, and other particles made of quarks. if energy is put into trying to pull quarks apart, the strong field does not simply weaken in the familiar way. Instead, the energy in the field can become large enough to produce new quark-antiquark pairs. The result is not a lonely isolated quark, but new bound particles. This is very different from electromagnetism. Two electric charges can be separated, and the electromagnetic force weakens with distance. With quarks, the strong interaction behaves in a way that keeps them bound. Inside protons and neutrons, quarks are always part of a dynamic field system. They are not little beads sitting calmly in a bag. They are constantly interacting through gluons, with energy moving through the fields that bind them. Yet quantum chromodynamics has another surprising feature. At extremely short distances, quarks behave more freely. This is called asymptotic freedom. David Gross, Frank Wilczek, and David Politzer developed the theory behind this discovery in the 1970s. It showed that the strong force becomes weaker when quarks are extremely close together, even though it becomes confining at larger distances. Deep inside a proton, at very short ranges, quarks can act almost like free particles for brief moments. Try to separate them far enough, however, and the strong force asserts itself again. This combination is strange but essential. Quarks are tightly confined inside particles, yet within very small distances they can behave with surprising freedom. The proton is therefore not a simple object. It is a restless system of quark fields, gluon fields, energy, motion, and confinement. It is stable enough to build atoms, chemistry, planets, oceans, and the quiet comfort of a mug sitting beside a bed, but inside it there is an intense quantum field structure. This is where mass becomes especially interesting. The individual up quarks and down quarks inside protons and neutrons get some of their mass through the Higgs field, but their masses are small compared with the mass of the proton or neutron as a whole. Most of the mass of a proton comes from the energy of the strong force field and the motion of quarks and gluons inside it. Because energy and mass are deeply related in relativity, that field energy contributes to the mass we measure. So the weight of ordinary matter is not simply the total mass of tiny ingredients added together. It is largely the mass of confined energy. The strong nuclear force does not merely glue matter together. It helps give matter much of its substance. The heaviness of the everyday world comes in large part from the activity of quantum fields inside atomic nuclei. This is a remarkable correction to the common picture. It is tempting to imagine mass as something stored inside particles like water in a bottle. But much of the mass in ordinary matter comes from relationships, motion, binding, and field energy. The proton is not heavy simply because its quarks are heavy. It is heavy because the strong field inside it is energetic. Quantum chromodynamics is difficult to calculate in many situations because the strong force does not always allow the neat approximation methods that work so well in quantum electrodynamics. When the interaction is strong, ordinary calculation becomes extremely challenging. One major approach is lattice quantum chromodynamics. In this method, space and time are represented as a grid for computational purposes, allowing powerful computers to simulate the behavior of quarks and gluons. It is not a perfect little picture of reality chopped into cubes, but a practical mathematical tool for studying a deeply complex field theory. Through these methods, physicists can explore how protons, neutrons, and other strongly interacting particles get their properties. The work is demanding, but it has made quantum chromodynamics one of the great successes of modern field theory. The deeper lesson is that fields do not merely decorate matter. They are not invisible accessories wrapped around particles after the important work is done. In the strong force, fields provide structure, confinement, motion, and much of the mass of ordinary matter. The solid world depends on something profoundly non-solid. restless quantum fields inside the heart of every atomic nucleus. A stone feels heavy because Earth pulls on it through gravity. But the stone has the mass that gravity acts upon largely because of strong field energy locked inside protons and neutrons. Beneath the stillness of matter is not a pile of tiny quiet objects, but a dynamic system of quarks, gluons, color charge, confinement, and energy. The ordinary weight of the world is in part the hidden weight of fields. The strong force holds quarks together with extraordinary power, binding them into protons and neutrons and giving ordinary matter much of its hidden mass. But not every force in the standard model is mainly about holding things in place. Some forces allow things to change, some are less like glue and more like a quiet doorway from one identity to another. That is where the weak nuclear force enters. The weak force is responsible for certain particle transformations. It does not simply attract or repel in the everyday sense. It can change one kind of particle into another, while still obeying the deep conservation laws of physics. It is involved in radioactive decay, in processes inside stars, and in the strange, nearly invisible world of neutrinos. It is called weak because, at ordinary energies and distances, its effects are much less obvious than electromagnetism or the strong nuclear force. But weak does not mean unimportant. A whisper can still change the plot. One of the classic examples is beta decay. In beta decay, an unstable atomic nucleus changes because a neutron can transform into a proton under suitable conditions. During this process, an electron and an antineutrino are emitted. At the deeper quark level, this happens because one of the neutron's down quarks changes into an up quark. Since a neutron contains two down quarks and one up quark, and a proton contains two up quarks and one down quark, that single quark transformation changes the identity of the whole particle. This is a very different kind of behavior from the strong force. The strong force binds quarks together. The weak force can alter the kind of quark involved. It allows matter to reorganize at a fundamental level. In ordinary language, it is as though one ingredient inside the neutron quietly changes role, and the entire particle becomes something else. The particles associated with the weak interaction are the W bosons and Z boson. They are massive carriers of the weak force. The W bosons are involved in processes where electric charge changes, such as the transformation of a down quark into an up quark during beta decay. The Z boson is involved in neutral weak interactions, where certain particles interact without changing electric charge. These bosons are much heavier than protons or neutrons, which helps explain why the weak force acts over an extremely short range. This short range is one reason the weak force can seem hidden. Electromagnetism reaches across large distances because the photon has no mass. Gravity, though far weaker between individual particles, also reaches across enormous distances. The weak force is different. Its heavy carriers mean its influence is confined to tiny scales inside atomic nuclei and particle interactions. It does not shape the everyday world in the obvious way light, electricity, or magnetism do. Yet without it, the universe would be profoundly different. The weak force has a deep connection to stars. In the Sun, nuclear fusion begins with protons interacting in a way that eventually allows hydrogen to become helium. One crucial step requires the weak interaction, because a proton must effectively be converted into a neutron as part of forming deuterium, a heavier form of hydrogen. This process also produces a positron and a neutrino. It happens slowly, which is fortunate. If the Sun burned through its fuel too quickly, Earth would not have enjoyed billions of years of steady sunlight, and life would have had a much shorter appointment with chemistry. So, the weak force helps regulate the pace of stellar burning. It is part of why stars like the Sun shine steadily over immense stretches of time. It is also responsible for producing many of the neutrinos that stream outward from the Sun. These solar neutrinos pass through space, through Earth, and through human bodies in enormous numbers every second, almost never interacting. They're among the quietest messengers in physics. Neutrinos are deeply tied to the weak interaction because they do not feel the electromagnetic force, and they do not feel the strong nuclear force. They interact through the weak force and through gravity, though gravity is incredibly feeble at the particle scale. This makes neutrinos extremely difficult to detect. They can pass through light years of matter with only a small chance of interaction. Detecting them requires vast instruments, patient observation, and a willingness to listen for the faintest possible knock on the door. The study of the weak force began long before the modern Standard Model had its full shape. Enrico Fermi developed an early theory of beta decay in the 1930s. Fermi's theory treated beta decay as a direct interaction involving the neutron, proton, electron, and neutrino. It was not the final picture, because the later electroweak theory revealed the role of the W and Z bosons. But Fermi's work was a crucial step. It gave physicists a mathematical way to describe weak processes and helped establish beta decay as a central clue to the deeper structure of particle physics. The weak force also became part of a larger unification. In the modern Standard Model, electromagnetism and the weak interaction are described together through electroweak theory. At high energies, they are understood as different expressions of a more unified framework. At the lower energies of the familiar world, the Higgs field and spontaneous symmetry breaking make them appear very different. Electromagnetism has a massless photon and long range. The weak force has massive W and Z bosons and an extremely short range. This is another place where quantum field theory reveals hidden order beneath apparent complexity. The weak force may seem like a specialized interaction involved only in rare nuclear events, but it is tied to symmetry, the Higgs field, particle masses, and the way matter can transform. It explains why certain unstable particles decay. It helps stars shine. It connects to neutrinos, some of the most elusive particles in the universe. The weak interaction completes an important part of the field picture. Electromagnetism shapes atoms, chemistry, light, and touch. The strong force binds quarks and gives nuclei much of their mass. The weak force allows particles to change identity, opening pathways for radioactive decay and stellar fusion. It is not merely a small correction added to the side of physics. It is one of the fundamental ways fields allow the universe to evolve. A neutron becoming a proton may sound like a tiny event, hidden far below ordinary perception. But changes like that help shape elements, stars, radiation, and the flow of energy through the cosmos. The weak force reminds us that reality is not built only from things that hold together. It is also built from transformations, from permitted changes, from fields that allow one particle to become another, while the deeper laws remain intact. The fields of quantum field theory are not only important inside laboratories, atoms, and particle accelerators, they also belong to the story of the whole universe. If modern physics is right, the early cosmos was not simply a hot cloud of particles flying through space. It was a seething state of fields, energy, radiation, and rapidly changing conditions, where particles could appear, disappear, transform, and interact in ways that are almost impossible to recreate today. The early universe was much hotter and denser than the universe around us now. As space expanded, the universe cooled, but in its earlier stages the energies were so high that the familiar boundaries between particles and forces may not have looked the way they do now. The calm, cool cosmos of stars and galaxies came later. Before that, reality was closer to an extreme quantum field environment, a place where the ingredients of matter were not yet settled into the quiet arrangements that eventually became atoms, planets, and sleepy creatures wondering why physics always gets weird just when it was becoming peaceful. In such conditions, particle creation and annihilation would have been normal. Energy could become particle excitations of fields, and particle excitations could disappear back into other forms of energy. Matter and antimatter could be produced in pairs. Particles could collide, transform, decay, and be replaced by other particles as long as the conservation laws were obeyed. The universe was not a fixed collection of little objects. It was a hot, dynamic system of interacting fields. This is where quantum field theory becomes essential to cosmology. It provides the language for describing how particles behave when energies are high enough for creation and annihilation to matter. It helps physicists understand how the early universe cooled from a dense, energetic state into a cosmos where certain particles became stable, certain interactions separated in behavior, and matter eventually found the long road toward atoms. One of the most important ideas connecting fields to the early universe is cosmic inflation. Inflation is a theory proposing that the universe underwent a very brief period of extraordinarily rapid expansion extremely early in its history. Alan Guth introduced a major early version of inflation in 1980, and André Linde developed influential later versions. The idea was not added simply to make the universe sound more dramatic, though it certainly manages that without much effort. Inflation was proposed to explain real puzzles in cosmology, including why the observable universe looks so smooth and similar in all directions, and why its geometry appears so close to flat. In many inflationary models, this rapid expansion is driven by a field-like mechanism, often discussed as an inflaton field. The exact nature of this field has not been identified, and the inflaton is not part of the confirmed standard model in the way the electron field or Higgs field is, but the idea shows how field thinking reaches beyond particle physics into the structure of cosmic history. A field, in the right state, may have shaped the expansion of space itself. During inflation, tiny quantum fluctuations may have been stretched to enormous scales. This is one of the most striking ideas in modern cosmology. A fluctuation that began as a minute quantum variation in a field could be enlarged by rapid cosmic expansion until it became a slight difference in density across space. Those tiny differences may later have helped seed the formation of galaxies, galaxy clusters, and the large-scale structure of the universe. This does not mean a galaxy is simply a quantum fluctuation wearing a dramatic costume. Gravity, dark matter, gas dynamics, star formation, and billions of years of evolution all matter enormously. But inflation offers a way to connect the smallest possible disturbances to the largest visible patterns. The seeds of cosmic structure may have begun as quantum variations, later amplified by expansion and sculpted by gravity. The universe, in this picture, carries the faint memory of quantum fields across the sky. One of the strongest observational windows into the early universe is the cosmic microwave background. This is the oldest widely observed light in the universe, released when the cosmos had cooled enough for electrons and atomic nuclei to combine into neutral atoms. Before that time, light scattered constantly from free electrons, making the universe opaque. After neutral atoms formed, light could travel freely. That ancient light has been stretched by cosmic expansion into microwave radiation, filling the sky in every direction. The cosmic microwave background is not perfectly uniform. It contains tiny temperature variations, little differences from place to place. These variations are extremely small, but they are crucial. They are like a faint fossil pattern from the early universe, revealing the seeds from which later cosmic structure grew. The COBE mission first measured key features of this radiation with great importance. The WMAP mission later mapped it in much greater detail. The Planck mission refined the measurements further, giving cosmologists an extraordinarily precise view of the young universe's structure. These observations support the broad picture of a hot early universe that expanded and cooled, and they are consistent with many predictions associated with inflation. But the story is not finished. The exact nature of inflation remains an active area of research. Physicists do not yet know whether inflation happened in precisely the way the simplest models describe. They do not know what field, if any, drove it. They do not know how it fits into a deeper theory that also includes gravity at quantum scales. The evidence is suggestive and powerful, but not a final closing of the book. This uncertainty is important because it keeps the science honest. Quantum field theory is extraordinarily successful within the Standard Model, and field ideas are deeply influential in cosmology. But not every field discussed in early universe theory has been confirmed as a real physical field in the same direct way as the electromagnetic field or the Higgs field. Some remain theoretical proposals, tested indirectly through their consequences and judged by how well they match observations. Still, the connection between quantum fields and the early universe is profound. This same general language that describes particle creation in accelerators also helps describe the hot young cosmos. The same idea of fluctuations in fields may help explain why the universe is not perfectly smooth. The same principle that fields can store energy and shape particles may extend to the expansion of space itself. The modern universe looks calm by comparison. Galaxies drift through enormous darkness. Stars burn steadily. Atoms hold together. Empty space appears quiet. But in the earliest moments, fields may have been the main actors in a cosmic transformation, creating particles, guiding interactions, driving expansion, and planting the first tiny irregularities that gravity would later grow into structure. The large universe and the quantum universe are often imagined as opposites, one unimaginably vast and the other unimaginably small. But the early universe brings them together. The oldest light in the sky may preserve traces of field behavior from a time when the entire observable cosmos was hot, dense, and changing rapidly. The galaxies scattered across space may owe their beginnings to tiny variations in fields, and the quiet darkness between stars may still carry the afterglow of a universe shaped, from its earliest moments, by quantum fields. Gravity is the force that feels most familiar, because it never really leaves the room. It holds feet to the ground, keeps oceans wrapped around Earth, guides the moon around the planet and gathers stars into galaxies. It is gentle enough that a small fridge magnet can defeat the pull of the entire Earth on a paperclip, which feels slightly disrespectful to the planet. Yet across cosmic distances, gravity shapes the largest structures in the universe, and still gravity does not fit neatly into quantum field theory. The Standard Model is a quantum field theory framework. It describes the electromagnetic force, the strong nuclear force, and the weak nuclear force through fields and their quantum excitations. It gives physicists a powerful way to describe electrons, quarks, photons, gluons, neutrinos, the Higgs field, and many other pieces of the subatomic world. It is precise, tested, and extraordinarily successful. Gravity sits outside that framework. At present, gravity is best described by Albert Einstein's general relativity. Published in 1915, general relativity changed the meaning of gravity. In Isaac Newton's older picture, gravity could be described as a force acting between masses. Earth pulls on the moon, the sun pulls on Earth, objects attract one another. This description works beautifully in many everyday and astronomical situations. It can calculate orbits, tides, falling objects, and planetary motion with great accuracy. But Einstein's theory went deeper. In general relativity, gravity is not treated as a conventional force in the same way as electromagnetism. It is the curvature of space-time. Mass and energy shape the geometry of space-time, and objects move along paths determined by that geometry. Earth orbits the Sun not because an invisible string pulls it inward, but because the Sun curves space-time around it, and Earth follows the straightest possible path through that curved geometry. This picture has been tested in many ways. It explains the bending of starlight by the Sun, the shifting orbit of Mercury, the slowing of time in stronger gravitational fields, gravitational waves, and the behavior of objects near black holes. General relativity is one of the most beautiful theories in science. It turns gravity from a force acting inside space-time into a feature of space-time itself. That is exactly why it is so hard to combine with quantum field theory. Quantum field theory usually assumes that fields exist on a background of space-time. The fields fluctuate, interact, and produce particles, while space-time provides the stage on which the theory is written. But general relativity says the stage is not fixed. Space-time is dynamic. It bends, stretches, evolves, and responds to energy and matter. Trying to make a quantum theory of gravity means trying to quantize not just something inside space-time, but space-time geometry itself. At ordinary energies, this problem can be avoided. The standard model works extremely well for particle physics. General relativity works extremely well for planets, stars, galaxies, gravitational waves, and black holes in many situations. Most of the time, each theory can operate in its own kingdom, politely ignoring the other like neighbours who share a fence but not a conversation. The difficulty appears when both quantum effect and strong gravity become important at once. This may happen near the centre of black holes, in the earliest moments of the universe, or at distances close to the Planck scale. The Planck scale is unimaginably tiny, far smaller than an atom, far smaller than a proton, and far beyond anything current particle accelerators can directly probe. It is often described as the scale where quantum effects of gravity may become unavoidable. At those extremes, the usual separation between quantum fields and classical spacetime begins to fail. A complete theory would need to explain what happens when spacetime itself has quantum properties. It would need to describe gravity in a way that respects quantum mechanics, while also preserving the central insights of general relativity. So far, no experimentally confirmed final theory has done this. One partial approach is called semi-classical gravity. In this approach, quantum fields are studied on a classical curved spacetime background. Spacetime is still treated using general relativity, but the fields living on that spacetime are quantum. This is not a complete theory of quantum gravity, but it can reveal important effects where quantum field theory and gravity meet. Stephen Hawking's work on black hole radiation is one of the most famous examples. In the 1970s, Hawking showed that when quantum fields are considered near the curved spacetime around a black hole holes should not be perfectly black. They can emit a faint thermal radiation, now called Hawking radiation. For large astrophysical black holes, this radiation is extraordinarily weak, far too faint to detect with current methods, but conceptually it was revolutionary. Hawking radiation suggested that black holes have temperature. It connected quantum field theory, gravity, thermodynamics, and information in a way that still challenges physicists. A black hole, once imagined as a one-way cosmic prison from which nothing could escape, became part of a deeper puzzle about entropy, radiation, and the fate of information. It was a meeting point between two great theories, but also a sign that the meeting was not yet complete. The unresolved problem is known as quantum gravity. A successful theory of quantum gravity would explain gravity in quantum terms and show how general relativity emerges in the appropriate limit. It would need to handle black hole interiors, the earliest universe, and the deeper structure of space-time. It would also need to make contact with observation or experiment, which is difficult because the relevant scales are so extreme. Several candidate approaches exist. String theory suggests that the fundamental ingredients of reality may not be point-like particles, but tiny, extended objects whose different vibrational patterns correspond to different particles. In many forms, string theory naturally includes a quantum description of gravity. Loop quantum gravity takes a different path, attempting to quantize space-time geometry itself, suggesting that space may have a discrete structure at the smallest scales. Other ideas also exist, including causal dynamical triangulations, asymptotic safety, and emergent gravity proposals. None has yet become a confirmed complete theory of nature. This does not mean the work is empty or speculative in a careless sense. It means the problem is genuinely hard, and the evidence is not yet decisive. Physics has two extraordinary frameworks: quantum field theory for the subatomic world, and general relativity for gravity and space-time. Each is deeply successful. The difficulty is that they seem to speak different conceptual languages. This is an important limit to keep in view. Quantum field theory is one of the most powerful tools in science, but it is not the final answer to everything. It explains the known particles and three fundamental interactions with extraordinary precision. It gives mass, light, matter, decay, and nuclear structure a field-based language. Yet gravity remains different. Space-time itself does not slip easily into the same framework. The result is not failure, but a frontier. Gravity reminds physics that even its best theories have edges. The universe has allowed deep understanding, but not complete possession. At the places where black holes curve space-time beyond ordinary intuition, and where the early universe compresses energy into unimaginable density, quantum fields and gravity point toward a deeper theory still waiting to be fully understood. Quantum field theory can sound as though it belongs entirely to mathematics, hidden inside chalkboards, symbols, and long calculations that seem to have been designed specifically to frighten peaceful people. But it is not only an abstract theory. It is tested in laboratories, in detectors, in particle accelerators, and in observatories built to notice some of the faintest signals nature allows. The fields themselves are not photographed directly. No camera can simply take a picture of the electron field stretching through space, or the quark fields inside a proton, or the Higgs field quietly present everywhere. Instead, physicists test fields by studying their effects. They look at particles produced in collisions, tracks left through detectors, energy deposited in layers of instruments, decay products, and the statistical patterns that emerge from enormous numbers of events. This is an important part of the story. Quantum field theory does not survive because it sounds elegant. It survives because it repeatedly makes predictions that can be checked. It predicts how particles should scatter, how often certain decays should happen, what kinds of particles should appear at certain energies, and what patterns should be seen when matter is pushed into extreme conditions. The invisible becomes testable through consequences. Particle accelerators are among the most powerful tools for doing this. They take particles, often protons or electrons, accelerate them to very high energies, and collide them either with other particles or with fixed targets. At these energies, the collision is not like two tiny billiard balls smacking together in a neat little clack. It is more like concentrating energy into a very small region, allowing the underlying quantum fields to produce new excitations. Some of those excitations are familiar particles, Others may be heavier, unstable particles that decay almost immediately. The products of these collisions tell physicists about the fields involved. If a theory predicts a certain particle should exist, or that a certain interaction should happen with a particular probability, then collisions can test that prediction. It is not usually one dramatic event that settles the matter. Particle physics is rarely that theatrical, despite the machinery looking as though it might open a portal if left unsupervised. Instead, the evidence comes from huge numbers of events, carefully measured and compared with theoretical expectations. The most famous modern particle accelerator is the Large Hadron Collider at CERN, the European Organization for Nuclear Research near Geneva. It accelerates protons around a circular tunnel roughly 27 kilometers in circumference before bringing them into collision at enormous energies. Inside the detectors, the collisions produce sprays of particles, many of which are short-lived and must be reconstructed from what they decay into. The Large Hadron Collider is best known for its role in discovering the Higgs boson in 2012. That discovery was a major test of the Standard Model and of the Higgs field. The Higgs boson was not seen directly as a little glowing speck. It decayed too quickly. Instead, physicists looked for patterns in the particles produced after collisions, searching for an excess of events matching what a Higgs boson would be expected to produce. The evidence came from statistics, decay channels, energy measurements, and careful comparison with background processes. At the Large Hadron Collider, several major detector collaborations study different aspects of particle physics. ATLAS and CMS are large general-purpose detectors designed to investigate a wide range of high-energy collision events, including the Higgs boson, and searches for new physics beyond the Standard Model. LHCb focuses especially on particles containing bottom quarks, studying subtle differences between matter and antimatter and the behavior of heavy particles. ALICE studies heavy ion collisions where nuclei are smashed together to create conditions similar to the extremely hot dense state of matter that existed shortly after the Big Bang, known as quark-gluon plasma. These detectors are enormous and intricate, but their basic purpose is clear. They record traces. Charged particles curve through magnetic fields. Calorimeters measure deposited energy. Muon chambers identify particles that pass through outer layers. Silicon trackers reconstruct pairs with remarkable precision. From these different clues, physicists infer what particles were produced and what interactions occurred. Other facilities also play important roles. Fermilab in the United States has been central to particle physics for decades, including studies of neutrinos, quarks, and high-energy collisions. The discovery of the top quark at Fermilab in 1995 was a major confirmation of the Standard Model. SLAC National Accelerator Laboratory has been crucial in electron accelerator experiments and in the development of particle physics, including deep inelastic scattering experiments that helped reveal the quark structure of protons and neutrons. Brookhaven National Laboratory has contributed to studies of nuclear matter, heavy ion collisions, and the behavior of strongly interacting particles. Neutrino observatories test the field picture in another way. Neutrinos interact so rarely that detecting them requires huge volumes of material and long periods of observation. Facilities such as Super Kamiokande in Japan, the Sudbury Neutrino Observatory in Canada, and IceCube in Antarctica have studied neutrinos from the Sun, the atmosphere, reactors, accelerators, and distant cosmic sources. These experiments revealed, among other things, that neutrinos change flavor as they travel, a phenomenon called neutrino oscillation. That discovery showed that neutrinos have mass, something not included in the simplest original form of the Standard Model. This is how experimental physics keeps the theory honest. Some results confirm the Standard Model with extraordinary precision. Others reveal places where the model must be extended. The experiments do not merely admire the theory from a distance. They press on it, measure it, and sometimes expose its limits. A single collision event can be beautiful, but it is rarely enough. Quantum field theory predicts probabilities. It says how often different outcomes should occur across many trials. So physicists collect vast data sets, sometimes involving billions or even trillions of collision events. They search for patterns that rise above background noise. They ask whether a small bump in the data is a new particle, a known process, or simply a statistical fluctuation being slightly dramatic. This patient accumulation of evidence is one reason particle physics can be both strange and reliable. The theory speaks in fields and probabilities, but the tests are concrete. Detectors are built, particles are accelerated, signals are recorded, predictions are compared with data. In this way, invisible fields become part of experimental science. The electron field is tested through electron behavior, the electromagnetic field through photons and charged particles, quark and gluon fields through hadrons, jets, and nuclear matter, the Higgs field through the Higgs boson and its measured properties, the weak fields through decays, neutrinos, and short-lived heavy bosons. Quantum field theory is therefore not just a beautiful idea about what reality might be. It is a working description of nature that has survived some of the most careful experiments ever performed. Its fields may be invisible, but their footprints are everywhere in the data, waiting quietly in tracks, flashes, decays, and patterns. Quantum field theory changes the picture of reality in a quiet but radical way. It does not ask the familiar world to disappear. It does not say tables are imaginary, stars are unreal, or a cup of tea is merely a mathematical rumour with steam. The world remains solid enough for everyday life. But beneath that familiar surface, the theory says that nature is not best understood as empty space, filled with little permanent particles. It is better understood as fields and excitations. The older image is easy to picture. Space is a container. Particles are tiny objects inside it. Forces push and pull between them. This picture works well in many ordinary situations, and it has guided science beautifully for centuries. But when physics looks deeply enough, especially at high energies and tiny scales, the particle-only view becomes too narrow. Particles can be created. Particles can disappear. Matter can turn into radiation. Radiation can become matter. The vacuum itself has structure. Forces emerge from interactions between fields. The world behaves less like a collection of tiny beads and more like a restless set of fields capable of producing particle-like events. The electron field is one part of this view. Every electron is an excitation of that field. Electrons are not merely separate little objects that happen to resemble one another. They are identical because they arise from the same underlying field, following the same quantum rules everywhere in the universe. The electron in an atom, the electron in a wire, and the electron in a detector all belong to the same field-based reality. The photon field, or quantum electromagnetic field, gives the same deeper meaning to light. A photon is a quantum of the electromagnetic field. Light can travel as a wave, yet interact in discrete packets. It can cross space from a star, scatter from an atmosphere, reflect from a surface, or be absorbed by an atom. The colours of the world, the glow of a screen, the warmth of sunlight, and the tiny shifts in atomic energy levels all connect to electromagnetic field behaviour. The quark fields and gluon fields reveal another layer. Protons and neutrons are not simple solid lumps inside atomic nuclei. They are dynamic systems of quarks bound by gluons through the strong nuclear force. Quantum chromodynamics describes this world of color charge, confinement, and field energy. Much of the mass of ordinary matter does not come simply from the individual masses of quarks. It comes from the energy of the strong force inside protons and neutrons. The weight of matter is, in large part, the energy of fields held in stable patterns. The weak fields add transformation. Through the weak nuclear force, particles can change identity. A down quark can become an up quark. A neutron can decay into a proton under the right conditions. Neutrinos can slip through matter almost unnoticed, interacting so rarely that they seem almost ghost-like, despite being entirely real. The weak interaction helps stars shine over long timescales and plays a crucial role in radioactive decay. It shows that quantum fields do not merely hold things together. They allow nature to change. The Higgs field adds another quiet layer beneath what seems obvious. It is present throughout space, and many fundamental particles acquire mass through their interaction with it. The Higgs boson, discovered at CERN in 2012 by the ATLAS and CMS collaborations, is an excitation of that field. It confirmed that this invisible field was not just a mathematical convenience. It was part of the working structure of the physical world. Yet even here the story remains precise. The Higgs field helps explain the masses of many fundamental particles, but most everyday mass comes from strong force energy inside protons and neutrons. This is the field-based worldview at its most powerful. Solidity, light, chemical bonds, nuclear reactions, particle decay, and mass are no longer separate mysteries. They become different expressions of quantum fields and their interactions. A table feels solid because atoms resist compression through electromagnetic interactions and quantum rules. A star shines because nuclear processes, including weak interactions and electromagnetic radiation, allow energy to flow outward. A radioactive atom decays because field interactions permit one arrangement of particles to transform into another. A beam of light is an excitation of the electromagnetic field travelling across space. Even empty space changes meaning. The vacuum is not absolute nothingness. It is the lowest energy state of quantum fields. A region can contain no detectable particles and still possess field structure, constraints, and measurable effects. The Casimir effect and the Lamb shift show in different ways that empty space in quantum field theory is not just blank absence. It is a physical state. And yet quantum field theory is not the final theory of everything. Its success is enormous, but its edges are real. Gravity is still best described by Albert Einstein's general relativity, where gravity is the curvature of space-time rather than a force fitting neatly into the standard model. A complete theory of quantum gravity remains unknown. Dark matter has not been identified. Dark energy remains deeply mysterious. Neutrino masses require physics beyond the simplest original form of the standard model. The imbalance between matter and antimatter in the universe is still not fully explained. That honesty does not weaken quantum field theory. It makes its achievement clearer. Within its proper domain, it combines quantum mechanics, special relativity, symmetry, conservation laws, and experimental evidence into one of the most successful frameworks ever developed. It predicts subtle atomic shifts. It explains particle interactions. It guides collider experiments. It connects invisible fields to measurable tracks, flashes, decays, and probabilities. Its message is not that reality is vague or imaginary. It is almost the opposite. Reality is structured more deeply than ordinary experience suggests. The familiar objects of the world are stable, but their stability comes from field behavior. The particles of matter are real, but they are not necessarily the deepest ingredients. Empty space appears quiet, but it is not the same as nothing. The forces of nature seem like pushes and pulls, but underneath they are interactions between fields. So the world can still be trusted at the scale of hands, tables, lamps, and stars. It is solid enough, bright enough, and orderly enough to live in. But at its deepest tested layers, it is not a universe of tiny permanent objects moving through a silent void. It is a universe of fields, usually calm, sometimes excited, always governed by precise rules. The ordinary world is the surface expression of that hidden activity, a calm appearance resting on an invisible and restless field beneath everything. Quantum field theory, explained slowly, becomes less like a single idea and more like a quiet change in how reality is pictured. It is one of the most successful ways science has found to describe the hidden workings of matter, light, forces, and even empty space. It does not replace the world of tables, stars, atoms, and warm cups of tea. It shows that beneath those familiar things, nature is organized through fields, excitations, symmetries, and interactions. The path begins with classical fields, where Michael Faraday and James Clerk Maxwell helped reveal that invisible influences could have real structure. Then light refused to behave as a purely smooth wave, and early quantum discoveries from Max Planck, Albert Einstein, Niels Bohr, Louis de Broglie, Erwin Schrödinger, Werner Heisenberg, and Paul Dirac pushed physics into stranger territory. Particles became linked to waves, probabilities, uncertainty, antimatter, creation, and annihilation. From there, quantum fields became the deeper language. The electron field, photon field, quark fields, gluon fields, weak fields, and Higgs field turned particles into excitations and forces into interactions. The vacuum became not absolute nothingness, but the lowest energy state of fields. Quantum electrodynamics showed astonishing precision. The Standard Model brought quarks, leptons, gauge bosons, and the Higgs boson into one field-based framework. The strong force explained much of the hidden mass of matter, while the weak force allowed particles to change identity. Even the early universe may carry traces of quantum fields stretched across cosmic history. And yet the story remains unfinished. Gravity still resists a complete quantum field theory description. Dark matter, dark energy, neutrino masses, and physics beyond the Standard Model remain open questions. The edges of knowledge are still there, calm but unmistakable. So quantum field theory does not make reality less real. It makes it deeper. What looks like stillness may rest on fields. What feels solid may come from interactions. What seems empty may hold quiet structure. Beneath the ordinary surface of the universe there may be no perfect silence at all, only fields waiting in the dark.